Hello, everyone. Welcome to the August 2022 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll, speaking here from Santa Fe, New Mexico, where I'm doing one of my occasional visits to the Santa Fe Institute, where I'm a fractal faculty member. SFI, Santa Fe Institute, is, one of the world's most amazing places to just sit and talk and think and do research, full of multidisciplinary people with wonderful ideas who are willing to talk to each other, right? It's easy to get a bunch of people in a room with different perspectives, but here at SFI, they specialize in bringing together people who come together for the purpose of talking to people unlike them in whatever they do or whatever they think about. So it's a great environment to be in. It's also a target-rich environment for guests for the Mindscape podcast. Several former guests have been around. Jeffrey West, the ex-president of SFI, was one of our very first guests here at Mindscape, and a couple of potential future guests are also hanging around. One former guest who I saw a talk by is Simon DeDeo, who I know very well. Simon did a Mindscape podcast interview on explanation and what it means, but his real day job is social cognition and decision-making. So what you mean by this is how not just one person, but many people interacting with each other come to conclusions, making decisions. And since I have a rough informal policy of not repeating guests here at Mindscape, so even though that would be a great thing to talk about, I'll just briefly tell you the point of his paper to put some ideas into your head. What they did, Simon and his collaborators, was study Reddit. In particular, there's a subreddit called Change My View. Okay, so you have people here who have a particular point of view, a belief about something, and they want other people to try to change their minds about it. So you can imagine that some people are coming into this with their minds more or less unchangeable, and others are on the brink, on the precipice. They're not really sure what's going on. But what they were able to do was classify kinds of arguments that were presented in the Reddit threads. And then the great thing about the reason why they did it on Reddit is you can quantify whether it worked. People will tell you whether or not they have changed their minds on the basis of your argument. So they could go through and figure out which kinds of arguments most often worked. Deductive arguments, where you have some premises and then you logic your way into a conclusion. Inductive arguments, where you have many examples and draw a generalization of them, other things. So here's the answer. Deductive arguments never change people's minds. They're terrible. They maybe anti-change people's minds. And I think that's not surprising. I'm beginning to think that deductive arguments are overrated, not at the level of logic, where they're rock solid, but the level of talking to each other, right? Communicative rationality. Deductive arguments only work if you buy into the same premises, right? The deductive arguments say, if I have some premises, I can draw a conclusion. All of the work is done by picking the premises. The conclusion is usually pretty easy to draw. There's obviously, in some sense, all good mathematical proofs are either inductive or deductive. But that's a special example that's different than the sort of casual conversation kind of thing we're talking about here. What did work on Reddit is personal anecdotes, experience, where you say, I was in this kind of situation and I felt this, or I saw this, I experienced this, witnessed this particular piece of evidence. Those kinds of things did change people's minds. And I suspect, I talked to Simon afterward, I wonder if it's more respectable than it sounds. If you just say, well, I had a personal anecdote and that changed someone's mind, it sounds like we're not very logical reasoners, right? We're just swayed by anecdote and stories. And we are, but there's a sense in which, we come to our views of the world by abduction, by inference to the best explanation, which I talked about in the big picture. The views that we have about the world are not independent of each other. It's not that we pick some rock-solid foundational beliefs and then deduce truths from that. That's just not how human reasoning works, nor really should it work that way, because, again, where do your rock-solid foundational beliefs come from? Instead, we're Bayesians in some sense. We consider different hypothetical big picture views of how everything works, and we ask what, given everything that we know, is the best of those possible views. And so personal anecdotes, I have not actually looked at the data that Simon used, but it might be a way of saying that people are fitting in different facts about the world into a coherent picture in a way that is a little complex and subtle and shows up as personal anecdotes in those particular Reddit discussions. I don't know. He also looked at Less Wrong, the website, and found very similar solutions there. So it's not just a particularly localized Reddit phenomenon. Anyway, I thought I would bring that up because, of course, we're always talking to each other here at Mindscape, and maybe minds will occasionally change. Minds usually don't change because people usually are pretty happy with most of their views about the world. And it's completely unfair, I think, to just rate the rate at which people's minds are changing, because sometimes people are close to the precipice, like we said, of changing their minds, and other times they're quite comfortable. And you want to concentrate on those cases where people's minds are willing to be changed. And that might be the result of a whole bunch of hidden things in the past, right? You don't know that this last little straw that broke the camel's back was really the important one. People might be on a journey to changing their minds in a way that you're not aware about. But anyway, it's still useful to know what kinds of techniques work, and let's keep that in mind when we're thinking about how we should change our minds, whether we should change our own minds, and how we should go about talking to others. So with that, I will just remind you all what's going on here. We're doing the monthly Ask Me Anything episode for Mindscape. The questions are asked by Patreon supporters. So you can go to patreon.com/Sean M. Carroll, join up, $1 a episode or more if you want. Join our little community, and every month I will ask for questions. People leave them in a post, and I will pick out the questions I think I have something interesting to say about. There's too many. Can't do them all. Sorry about that. Usual apologies. But we generally get a very nice, wide variety of questions, and then I will answer them. And the many, many thanks to the Patreon supporters, because they voted to let these AMA episodes go public and just be regular episodes of Mindscape, even though they are supporting them. So we appreciate them for that. Join if you want. You don't have to if you don't want to. We're all here together anyway. So with that, let's go. Deepthi Amasurya says, the scholarship idea is amazing. This is Sean talking now. Let me back up to remind you, if you don't know already, that we have a Mindscape Big Picture Scholarship that you can contribute to. It's being crowdsourced. You can go to bold.org/scholarships/Mindscape. That's BOLD.org. And the idea is we're given money, and then we're going to choose one or more winners every year to get $10,000 toward their college education. And we're aiming at people who are interested in the big ideas, right? Not necessarily practical things. There's a lot of doctors and lawyers out there. That's great. We're aiming at people who are trying to think about physics, philosophy, biology, computer science, mathematics, trying to figure out the fundamental structure of reality. That is the goal. And especially if we can contribute to the education of lower income students, first generation students, underrepresented groups in these fields, that would be great. To give someone a chance to pursue these slightly impractical kinds of career paths is what we're trying to do. $10,000, a lot of money, but it could change somebody's life. So anyway, Deepthi says, what about setting up a scholarship foundation to encourage students to study physics, philosophy, artificial intelligence, etc.? Start small with a grad student working remotely a few hours a week, sorting out applications and sending you the more promising ones for careful scrutiny. The foundation can grow later. This way you're not at the mercy of an external organization with potential non-constant credibility. That's something that kind of sounds like a potentially good idea. It also sounds like an enormous amount of work, certainly something I would not set a graduate student to doing. One of the things about being a good advisor is you do not make your graduate students do things that are not furthering their education in some way. And also, I actually think that bold.org is quite credible. I did check them out before embarking on this partnership with them, and they seem, really dedicated to getting 100% of the donations into the pockets of the students. And also they do a lot of the work. I've noticed we have applications for the scholarship already. Many of the applications are, they're students who want to get a scholarship. That's great, but they're completely inappropriate for this scholarship. They're not tackling the particular kinds of questions that we're aiming at whatsoever. So I could, personally or hire someone to sift through that, but Bold will do that for me. So that's great. And I think it's actually going to be a pretty good setup. If we become, really big time, then it might change, but I doubt that will happen. We funded our first 10K scholarship, and I'm kind of hopeful that we can get another 10K scholarship funded this year, and then we'll see what happens next year. But I suspect that's the level at which this is going to happen, right? 1 or 2 scholarships per year, not a major thing where we're changing the lives of hundreds of people. Well, that would be great. You never know. I'll keep my mind open about that. Tarun says, you mentioned on your podcast with Max Tegmark that you would only give 50% credence to the level 2 multiverse. Eternal inflation plus string theory gives rise to multiple universes with different laws of physics. If we remove the string theory aspect and just focus on the idea of multiple universes, perhaps with the same laws of physics, would your credence be higher? If not, why is your credence relatively low for a theory that some physicists say is a natural conclusion of inflation plus quantum mechanics? Well, some physicists say lots of things. Some physicists say that the whole multiverse idea is completely crazy, right? I don't think that some physicists say is going to push my credences one way or the other, unless either all physicists say or the right physicists say, the physicists who understand this the best. And the physicists who understand this the best are not in agreement about it. Furthermore, I'm an expert. This is what I do for a living, so I have my own judgment, completely independent of what other physicists say. It's very possible that there is a multiverse, this kind of type 2 multiverse, where to me, what that means is there are regions connected to our space-time, but very, very far away, outside causal contact with us here in our part of the universe, where conditions are different. Okay, that's what I would mean by the type 2 multiverse. You can get it via eternal inflation and string theory, but maybe there's other ways to get it as well. And maybe inflation is correct and or string theory is correct, but in a way that doesn't give rise to a multiverse. All of these things are very, very open. Even though this is what I do for a living and I think about it and I take the ideas seriously, I don't get too caught up in my favorite ideas. I don't think that these speculations about times and places where we have no empirical evidence should be given too high credence. We should be open-minded about it. That's what the 50% credence sort of stands in for. It's just a way of saying maybe, maybe not. And there's no guarantee that even if string theory is right, which I'm not sure that it is, I'm not sure what my credence on that would be either, string theory could certainly be right without giving rise to this kind of multiverse. That's an active question within string theory. And I think that's different. If people want to ask, so why is my credence so high in many worlds? Many worlds is based on the Schrödinger equation, which has been very, very tested. That part of the theory is not speculative. And once you get into how to get rid of the other worlds, it's very hard to do. That's the speculative part. So to me, many worlds are just the default if you believe in the Schrödinger equation and wave functions. So it's a very different kind of credibility calculation than the many worlds, than the multiverse of cosmology, the type 2 multiverse. Bob Polk says, I'm a longtime follower of your work and a sometimes social scientist hooked by you on the curious domain of entropy. I've imagined asking several specific questions about how to correct for entropy's elusiveness in the practices of the social and political sciences. But for now, I simply want to ask more broadly, what might be entropy's greatest promises to the day-to-day experiences and practices in our social and political lives? More aspirationally, how might we one day use this knowledge to make our macro worlds a little wiser? Well, yeah, that's a good but slightly broad and vague question. Entropy is a very, very useful concrete concept in physics. And what typically happens is that you build up, either explicitly or implicitly, your knowledge in layers of reality, right? You can start with the physics level, the fundamental physics level. You can go to some emergent phenomenon where there are coarse-grained descriptions and you have equivalence classes and you can assign macro states which have an entropy. And then you have even higher levels of biology and psychology and social sciences and so forth. So a priori, there doesn't need to be any connection between the entropy that a physicist talks about and the social sciences, because you can do social science without knowing about the fundamental microphysics underlying everything. Now, there are two exceptions to that. So that was the caveat, but there's sort of two loopholes there that are worth exploring. One is, it is, of course, interesting to connect the different levels. We do think that you can talk about social science without knowing about the standard model of particle physics or even statistical mechanics or thermodynamics, but that doesn't mean that your study of the social sciences might not be usefully illuminated by thinking about how fundamental physics works. After all, social sciences don't violate the fundamental laws of physics. They are somehow a pattern that exists within the structures that are governed by the fundamental laws of physics, and maybe that can be useful, or maybe not. I don't actually have a concrete example of it being useful. The other way, which is probably closer to what you have in mind, is to think about studying social systems in ways that the entropy or other related concepts appear directly. This is part of what I'm trying to do with my questioning about the physics of democracy, right? To think about whether or not ideas that we get from physics can be usefully used either directly or just analogically in social science constructions. Entropy in particular, it's not clear that that's going to be a helpful concept because the dynamics that we're interested in are already irreversible, if you know what I mean. We've already taken into account that human beings burn up fuel and they, eat and metabolize and then radiate higher entropy stuff into the universe. That doesn't need to be an extra part of our social science calculation. That's already there in what it means to be a human being. So you sort of don't need to include it again in some very trivial sense. On the other hand, if you look at a larger level of sort of structures that are formed within human societies and conglomerations, maybe there are patterns of structure formation that can be usefully illuminated by thinking about what we learn from entropy or statistical mechanics. Now, I realize, Bob, I am being very, very vague here because I don't have any explicit constructions to give you. That is true. I don't. I'm not trying to hide all the good ideas from you here. I just want to sort of simultaneously get across some enthusiasm for the idea of trying to see if we can understand how organizations and higher level structures emerge and behave using ideas from physics, while at the same time remaining slightly skeptical in the sense that maybe it's not useful. I don't know. I'm not demanding that it's useful or insisting that it is or even giving you an explicit example of where it is. I'm just saying maybe it is. People should think about that. So that's the state at which I'm in right now. Sandro Stuckey says, I much enjoyed the episode with N.J. Enfield, but I'm skeptical of the premise that language is good for lawyers and not scientists. It suggests that scientists are somehow hyper-rational. Don't you think effective scientists use the full repertoire of human language to argue, persuade, tell stories, etc., for better or for worse? Sure, absolutely. And I don't think that Nick Enfield would disagree with that. Part of it is, of course, it's a great title. Language is good for lawyers, not scientists. If you come up with that title for your book, you're going to use it. It's just too good to be resisted. But he doesn't mean that, scientists shouldn't use language or that scientists are somehow perfect reasoners who might be able to communicate in a way that doesn't involve language at all. That is not the point. The point is that the structures of language and the way that they're used in our brains are naturally adapted to the purposes of persuasion and social contact. And those are the kinds of purposes that lawyers need in their everyday life. Whereas the kinds of purposes that scientists have of precisely and rigorously and unambiguously describing the world in very definite quantitative terms, that's just not what language is made for. That doesn't mean you can't use it anyway. It's all we got. That's how we communicate with each other. You can modify language. You can build on top of it. You can construct new notations, new vocabulary words, new ideas, and scientists do that all the time in an effort to try to be more and more clear about what they're saying. So, of course, scientists use language. The point is that don't be surprised when the concepts and constructions of natural language don't fit easily and comfortably and effectively with what scientists are trying to do. Ben Suttles says, I was listening to a baseball game when my favorite team went down in the 8th inning. I turned off the game in disappointment, but found out later that they came back for a walk-off win in the 9th. I was sad to have missed the excitement, but then I thought that the act of turning the radio back on to listen might have had some effect that could have interfered with the comeback. Are there any signals that can conceivably have affected an outcome happening 30 miles away within a 30-minute span? Baseball outcomes hinge on very minute differences in human movement, so I'm wondering if there's any plausible way for my minor action to have slightly tweaked the environment or nervous systems of the players to change the outcome. So I think I almost didn't answer this question because the short, immediate answer, which is probably right, is no. There is no plausible way for your movements or flicking off your radio to have an effect on the baseball game. But, this is the kind of question where maybe you have to think a little bit more carefully. So before we give it too much credibility, let's just say there's certainly no way that you could know that a certain kind of action in your living room 30 miles away is going to have an effect on what happens in a baseball game, okay? You can't decide to do something rather than something else in hopes that your team is going to have a comeback in the ninth inning, okay? So don't worry about your planning. This is not going to be relevant there. But the question is one of nonlinear dynamics and, in some sense, in chaos theory. I don't want to wed it to chaos theory too explicitly because there are quantitative measures of when things are chaotic and so forth that I don't want to invoke here, but there is a question of, many, many things are happening in the world, many, many little influences. And like you say, in certain cases, a very tiny influence can build up and become something big. And so all I'm trying to say here is that you would really have to think about it carefully to be 100% sure, or even 99.9999% sure, that a certain action, a macroscopic person-sized action 30 miles away, could not move the effect of a baseball game one way or the other. Change the twitching of someone's muscle just a little bit, or move a bat by a millimeter when it was swinging at the ball, can completely change the outcome of a game. That's what nonlinearity means, right? When physicists talk about linear systems, they mean a small change leads to a small effect, whereas a nonlinear system, a small change can lead to a large effect, okay? And there's lots of nonlinearities involved in systems like this. I know that Eric Schwitzgebel, who is a philosopher, has asked, whether or not small things you can do can lead to potentially infinite changes in the broad future, and he suspects that maybe they can. I'm highly, highly doubtful that that is true in this case, in this particular case, because the basic reasoning is whatever effect you do, even though there are nonlinear repercussions, they're damped out, right? You can't even hear what you're doing inside your house if someone is standing out on the lawn right outside. So 30 miles away, to imagine that impact really travels that far strains my imagination personally. I just want to be careful and say I can't guarantee that there couldn't be some tipping point that you could have triggered by that motion. Okay, I'm going to group together two questions. One is by Robert Ruxandrescu, who says, when we talk about black holes, we have the singularity surrounded by an event horizon. The singularity is not visible. But for a white hole, it seems like the singularity is accessible. It doesn't have an event horizon. You have access directly to the singularity, similarly to how we can look directly at the Big Bang. It behaves like a naked singularity. Doesn't this contradict the cosmic censorship conjecture? And if you were to travel outside of a white hole, would you pass both the singularity and some event horizon, or just the singularity with no event horizon? And then James Allen says the laws of physics are time reversible, but nothing comes out of a black hole. Does that mean some massively improbable set of initial conditions could be set up so that you start with a black hole, evolve it forward in time, and come back later to see, say, two rotating neutron stars? So both of these questions are about white holes, and there's two very important facts to remember here that will answer most of your questions about white holes. One fact is that a white hole is nothing more or less than a black hole run backward in time. Okay? It's not a different kind of thing. It's the same exact thing as a black hole, except that the singularity and the event horizon are in the past rather than in your future. The other thing to remember is, as I just hinted at, in a black hole, the singularity is not a point in space. It's a moment in time, and in particular, it's in the future. So when you say a naked singularity, neither white holes nor black holes qualify as naked singularities. Naked singularities are supposed to be singularities that are not surrounded by event horizons at all. If you think to yourself, is a white hole surrounded by an event horizon? Well, a white hole is just a black hole played backward in time. Is a black hole surrounded by an event horizon? Yes. Therefore, a white hole is. The difference is, what is the property that makes it a black hole event horizon? It's that when you cross into it, you cannot come out. Therefore, the property that makes a white hole event horizon is that once you cross out of it, you cannot go back in. And exactly like the black hole event horizon is in your future, the white hole event horizon is in your past. A naked singularity, on the other hand, is not supposed to be a moment in time, because a moment of time, you say, Robert says in the question, you can look directly back at the Big Bang, unlike a black hole. But in fact, in the space-time picture, the seeing, you're sort of imposing an arrow of time there, right? You're saying that I can see things in the past, but not in the future. There are still trajectories that go from your eyeball to the black hole singularity, but they just go into the future and then hit the black hole singularity. Likewise, there are trajectories from your eyeball to the white hole singularity. They just go back into the past, okay? A traditional naked singularity is literally a point in space. It is not a moment in time. It is what we call a time-like singularity, which is a funny way of, in physics speak, saying it's a point in space, not a moment in time. Moments in time are space-like, believe it or not. Points in space are time-like. So a naked singularity is one that you could literally travel to, visit, look at, and then go away. Neither a white hole singularity nor a black hole singularity are like that, okay? So it doesn't contradict the cosmic censorship conjecture. If you were to travel outside a white hole, the singularity is in your past. So either you're inside the event horizon, and then you will be in there for as long as you don't pass by it. Once you pass the event horizon, then no signals from, let me get this right. If you pass into the event horizon of a black hole, that is like passing out of the event horizon of a white hole. But of course, you also need to flip your past and your future, right? So when you're inside the event horizon of a black hole, no future of yours escapes from the singularity. When you're inside the event horizon of a white hole, that means no past of yours failed to hit the singularity. All of the signals that you are getting in your light cone come from the singularity of the white hole. Whereas when you pass outside the event horizon of the white hole, now there are some signals that do not come from the white hole singularity. And for James's picture, yes, there are absolutely massively improbable sets of initial conditions. So you start with a white hole. You call it a black hole, but it should be a white hole if it's backwards in time. And then you start with a white hole, you evolve forward in time, and you can see two rotating neutron stars, or for that matter, anything else, because the Big Bang is very much like a white hole. And in fact, the Big Bang does evolve into neutron stars and things like that. So there you go. Jeffrey Siegel says, very interesting conversation with John Quiggin on the information economy and reasons for market failures. One complication or feature that is hard to incorporate into models is the ingenuity of humans for finding unexpected ways to make a short-term profit. In the case of the information economy, it seems that although rational actors place a high priority on truth and accuracy, real humans can place value on parts of the information economy irrespective of absolute truth or accuracy. Similarly, speech is important for communication, but truth is not always a priority. Do models of the information economy include actors who make a profit off of the desire for interaction without considering truth or accuracy of the information? Well, sure, yes. I mean, I'm not an expert on models of the information economy, but the little that I know about economics assures me that the models do not imply that the actors are in any way dedicated to truth, justice, the American way, or anything like that. The actors in an economic model want to make money. They are rationally self-interested. They are not supposed to be or imagined to be moral in the sense that they would sacrifice themselves for the greater good, okay? The idea of a market economy, one of the ideas of a market economy, is that you can get outcomes for a large number of people, even if every individual is rationally self-interested. This is Adam Smith's claim. And he wasn't nearly the fundamentalist about markets that he is sometimes painted to be. He understood that there could be flaws there, but he pointed out that in some cases, everyone looking out for themselves can lead to a desirable outcome for everyone. Because, if I want to sell you a widget and you want to buy a widget, number one, I have to set the price so that you can afford it, and I'm competitive with other people who are trying to sell you widgets. But also, I have an interest in selling you a working widget, not one that will fail, because if I sell you one that will fail, next time you're going to buy from somebody else, okay? Here's where it becomes harder when it comes to information. Maybe the analogy to a working widget is supposed to be selling you true information. But it's clear that everyone wants a working widget. It is not clear that everyone wants true information. Sometimes people want information that makes them happy, right? Or that flatters their preconceptions, or that fits into their pre-existing worldview, etc. So this is why I think there's sort of a new kind of problem when it comes to the information economy. And I don't have any suggestions for solving it. I'm just sort of pointing it out. And I'm by far not the first person to point it out. But the criteria for the information that you're buying or acquiring being successful, what you're looking for, is a little bit different than truth, right? Whereas everyone can kind of agree that, the car runs in the way that it's supposed to when I buy it. Not everyone agrees on this bit of information is useful or not useful, true or false, etc. So I don't know what to do about that. I mean, obviously what we would like is to reward those information providers who provide accurate, useful information. I'm not quite sure what the best way to do that might be. Domas says, you keep mentioning Laplace's demon in your examples. However, in other cases, you said the world is not deterministic, excluding many worlds. It's probabilistic. So was Laplace wrong? His demon couldn't exist even theoretically. Well, I've written a lot about this, and you can Google determinism and my name and see things I've written about it. In our actual world, okay, that is to say, in the world of our experience, where I say us, I mean literally you and me. So not the God's eye view or the Laplace's demon eye view, the world that you and I actually live in, it is not deterministic. Full stop. That is what quantum mechanics tells us. So that's why I get slightly frustrated with people who try to argue against free will on the basis of the world being deterministic. It's just that their first premise is completely wrong. And sometimes they try to say, well, but the indeterminism is only small scale and it's all deterministic on the large scale. Again, completely wrong. There can be absolute amplifications of quantum probabilistic outcomes to macroscopic scales, okay? So there's absolutely a question about whether or not there is a bigger picture, there is a God's eye view in which things are deterministic. And a many worlds person, or for that matter, a pilot wave person, would say, yes, there is such a bigger idea. So what does this have to do with Laplace's demon? Laplace's demon was never supposed to be practical. Laplace's demon is not even supposed to be something that in principle you could imagine building. Laplace's demon is supposed to be a colorful metaphorical way of talking about deterministic evolution. That's all it's supposed to be. So people talk about, what does Laplace's demon know or how does it think? I think that they're missing the point. The point is that the future is determined if the laws of physics are deterministic. That's the entire point. And in the pictures we're talking about here, it very well might be true for the many worlds. The set of worlds altogether might very well be determined. That is not accessible to us here, mere human beings. So I still think that Laplace's demon is very useful as what it's supposed to be, a metaphorical thought experiment to talk about the implications of determinism. But of course, you have to always be accurate about whether the world is deterministic or not. For real world, what we know kinds of purposes, the world is not deterministic. But then again, for real world, what we know kinds of purposes, you were never Laplace's demon anyway, so I'm not sure what the change is supposed to be given by quantum mechanics. Peter Bamber says, physicists used to hope for a grand unification of all four forces. However, gravity is distorted space-time whilst the other three are quantum fields. These seem to be completely different. Is there a reason to suppose that a quantum theory of gravity would be sufficiently similar to the quantum field theory of the other three forces that grand unification is the way the universe works? Put another way, is it possible that gravity will remain distinct from the other three forces even when a quantum theory of gravity is established? I will repeat my mantra that I often say here in AMA episodes and elsewhere. Any question that is phrased of the form, is it possible that, in physics, will usually be answered with yes, it is possible. That's not really the interesting question. We want to have some credences. We want to know how reasonable it is to think these things. So for one thing, just for your benefit, the phrase grand unification is a technical term within physics that does not refer to gravity. Grand unification was the attempt to unify the electromagnetic force, the weak force, and the strong nuclear force. It did not include gravity, okay? That's why Stephen Hawking joked that they're neither grand nor unified nor theories, the grand unified theories, because they don't include gravity. That's why when string theory proposed to be a quantum theory of gravity and all the other forces at once, they invented the phrase theory of everything to be that. It's a step beyond grand unification. And, the answer is we don't know. We don't know how it's going to turn out. You can't be too confident, I don't think, one way or the other. It is true that gravity is different than the other forces. But to say gravity is distorted space-time whilst the other three are quantum fields is not completely true. Gravity is also a field, classically. What we don't know is if you can take that classical theory and just quantize it in the same way that you quantize the other theories. As classical theories, there are a lot of resemblances between general relativity and the gauge theories that we have for the other forces of nature. They're based on certain local symmetries, they're field theories, et cetera, et cetera. So it's a perfectly reasonable guess that you can group them together. But it's also different. Even though there's similarities, the similarities are not 100%. The fact that gravity is so intimately connected to the nature of space-time is different between gravity and the other forces. So maybe it's not the same. And as I like to point out, it's completely reasonable to imagine that in the case of the other forces, we just got lucky with this whole idea that you could start with a classical theory and then quantize it. There's no guarantee that a particular quantum mechanical model can be reached by starting with a classical theory and quantizing it. So that might be the case for gravity, that you shouldn't start with a classical general relativity or string theory or anything else, quantize it and hope to get the right answer. So the answer is we should be open-minded about all these different possibilities. String theory, I keep saying, has done a lot of great things. There's something that smells right about string theory, but it might eventually not be how nature works. That's also completely possible. So, the two extremes that think that string theory is obviously right and we should give up on everything else versus the extreme that thinks that string theory has obviously failed and we should not study it anymore, I think that both of those are off the mark pretty dramatically. Schleier says, I hope I'm not pronouncing that correctly, in your first AMA in 2018, you called yourself a believer that technological progress is still in its beginning states. Can you talk about your reasons for thinking this and whether your confidence has changed as various limits to industrial growth and stability have become more evident? More generally, the modern era is a highly anomalous brief period in our species' long history. Wouldn't one expect a system to revert back to the norm rather than getting more anomalous? I mean, yeah, this is a good question. And when someone like me says something like, technological progress is still in its beginning states, that's obviously a wild extrapolation that might turn out to be completely wrong. But no, the last 4 years have not changed my mind about this particular one. And the reason is just because I think the technological progress, it's not just a kind of simple-minded extrapolation of rates, right? I think there's no good intellectual reason to say, well, things have been going for a certain rate for a certain time. Let's just extrapolate it for the next century or whatever. You have to be a little bit more clueful than that. You need to think in particular about what kinds of technological progress are possible. And to make a very complicated argument very, very oversimplified, the reason why I think that technological progress is in its beginning states is because it's mostly been based on physics. Most of our technological progress, physics and chemistry, I would say, has to do with manipulating matter at a fairly simple level of molecules and atoms and their combined kind of materials and states of matter. All of the high-impact stuff, or much of the high-impact stuff, will be in biology, right? Biology is way more complicated than physics is, and we're very not good right now at manipulating it. That's why I think that there's still an enormous amount of room to go. I mean, there's still an enormous amount of room to go in the physics side of things. Building better computers is, in some sense, a physics/engineering problem, and there's a lot of room to build better computers, quantum computing just being one kind of case. But things like synthetic biology and gene editing and stuff like that have just enormous room to grow in. So I would not be at all surprised. I can't guarantee, but I would not be at all surprised if 500 years from now, the century in the future of today is thought to be much more technologically rich than the century that we have just experienced. We'll see. I'll be dead. Unless biologists cure aging, in which maybe a case I'll be around. Rob Patro says, you recently tweeted about the walkout of the medical students at the University of Michigan's White Coat ceremony, where the university had platformed an anti-abortion speaker. You noted that you agree with this form of protest, a silent walkout, and I completely concur. My question is, where do you think it makes sense to draw a line, particularly in the context of academic talks or talks at universities, between acceptable protests that should be respected and unacceptable protests that should be protected against? For example, I think most reasonable people agree that hurling rotten eggs or tomatoes at the speaker would have been unacceptable. So this is a great question, but I don't necessarily think that there is once and for all a clean-cut answer. In fact, I think that part of the way to go wrong here is to oversimplify and try to overclarify very complicated questions. It's not to say that you shouldn't be serious about thinking about how to draw the line, but you can't be too dogmatic about having drawn the line and then declaring victory and never rethinking what you've just said. So anyway, for those of you who don't know what we're talking about here, there was a protest at the University of Michigan where there was a speaker invited by the university or some department within the university to talk to graduating students, and the speaker was notably anti-abortion. And it's a medical school, as I recall, or at least some medical students. And at a time when the right to get an abortion in the United States had just been dramatically undermined, many medical students thought that was not appropriate, so they walked out of the speaker's talk. And other people have come along. What I was responding to on Twitter was, a very reasonable, thoughtful point of view, which was we need in a democratic society to be able to talk with and have dialogue with people we disagree with. We can't just turn our backs on them and walk out. And as a statement of, lofty principle, I completely agree with that. I very much agree that we need to be able to talk to, have dialogues with people we disagree with, even people we disagree with by a lot politically. But I just don't think that principle applies here because there wasn't a dialogue going on. One person was giving a speech and the other people were supposed to sit quietly, okay? That's not a dialogue. And even though I do think that it is important to have dialogue with people you disagree with, protests are also important. And I think that, there's sort of an ideal speech situation where we all come together, we all agree to speak reasonably to each other over our disagreements and try to overcome them and see where we can find common ground. And that kind of situation is what we should aim for. But we can also realize that situation does not always happen. And so sometimes other kinds of actions are completely appropriate. I think that walking out is one of the most mild and unobjectionable kinds of protests. Even if, the speech that the speaker was giving was not about abortion, but these people in the audience thought that this issue was sufficiently important that they wanted to make a statement. And that's what that protest did in a fairly innocuous way. So I said on Twitter, half jokingly, that I was giving a talk on quantum mechanics later that week. And if anyone wanted to come and walk out on it silently walk out on the speech because I am pro-abortion, pro-choice, then they were welcome to do that. I do not mind. I respect their ability to do that. Now, what about other kinds of protests? This is Rob's question, where it's more intrusive, more disruptive in some sense. And, I think, again, you have to actually take the circumstances into consideration. So let me back up a little bit, because I think that there's a general tendency here to hide one's substantive commitments behind procedural arguments, right? There's the substance, are you pro-life or pro-choice? And there's the procedure. Do we talk to each other? How do we protest? Things like that. And even the people who said that the protest was wrong said, of course, if the person talking were like a Nazi or a eugenicist or something like that, a white nationalist, then you could walk out. And that kind of gives the game away, doesn't it? Because they're saying that in their mind, this particular issue, the ability for women to choose to get an abortion, wasn't that big a deal compared to racism or Nazism or whatever. And my response is, to some people it's a very big deal. And more generally, we can't kind of dance around the question of how big a deal it is. There will always be some kinds of disagreement that are so dramatic, so important, so valuable to people that you can go beyond the ordinary norms of polite speech. So there are times, I think, that would be completely appropriate to disrupt a speaker. But I'm just saying that as a matter of principle. I think that as a matter of practice, that should be very, very rare. That should be only reserved for the most extreme possibilities. In particular, in practice, at a place like a university, I think that what matters are the protesters part of the group who is giving the person a platform? So in other words, if I'm a student at a university and the university as a whole invites a speaker, then I think that there's a little bit more room for protest there. That's a perfectly legitimate thing to protest. Hopefully not in a disruptive way, because I would always err on the side of letting people talk. But I would listen to arguments in favor of disruption to see whether or not they were persuasive. Whereas if some subgroup, if some, club or class or whatever on campus wanted to invite a speaker in, then I would say that you should just essentially never try to disrupt that if you're not a member of that group, right? You should let other people listen to who they want to listen to, even if the people are really bad. And whenever I say things like this all the time, and people always say, yes, I agree, unless they're really bad. and I actually mean it even if they're really bad. Let people listen to really bad people. That's exactly the situation where we should try to fight speech with speech, okay? But if you are being forced as a member of a bigger community to support, implicitly or explicitly the speech of some person who is really reprehensible, then maybe you have a right to be a little bit more disruptive. Again, I know that I'm being fuzzy and vague here. That's because I think it is fuzzy and vague. I think that it's going to be a case-by-case basis, and this desire to come up with the clear, bright line ahead of time is what leads to a lot of mistakes. I think we should use our judgments. I think that's okay. That's what politics is like, and I think politics is very, very important. Avanish Narla says, what do you think the tradition of physics can contribute to the study of human society and democracy? Is it the approach, like phenomenology or reductivism, the tools, like interaction models or flow analysis, or the attitude, first-order understanding versus order one understanding? Yeah, I think all of these things can contribute. I think two things. I think that physicists have a deserved reputation for not taking seriously the intricacies and difficulties and special challenges of other fields, okay? I know perfectly well physicists have a big, bad, well-deserved reputation for swanning in and saying, what you're doing doesn't look that hard, let me clean it up and solve it all, okay? And that's bad, and it generally results not from being a physicist, but from not affording these other fields of human inquiry the same respect that they afford to physics itself. It took time to learn to be a physicist, right? You made mistakes, you had to learn a lot, you had to figure out what was sensible, what was not sensible, what the techniques were, what the challenges were. You should spend that much time trying to learn about other fields as well if you think that you can contribute to them. So that's one side of the coin. The other side is, nevertheless, we should try. We should try to have all sorts of interdisciplinary engagement. And that consists both of individuals who can talk more than one disciplinary language, and also, even more importantly, actual interactions between people from different disciplines talking to each other. So in particular, what can physics contribute to the study of human society and democracy? All of the things you mentioned. Physics is really, really good at a particular kind of analysis, right? The spherical cow, boiling complicated situations down to very, very simplified essences, and then solving those essences purely and crisply and cleanly and quantitatively. The question is always, can you then go back from the simplified model to the messy reality of the world? People like Galileo were geniuses at doing that. Einstein also. We're really like geniuses at picking out in some complicated situation exactly what the simple, important essences were, and then extrapolating back and getting true conclusions about the messy real world. That's what physics is good at. It's much harder to do that in social sciences, in human society, philosophy, and literature, all those things, okay? That's not to say it can't be done. That's not to say that it is impossible or not worth trying to do. It's just that you have to keep your wits about you a little bit more carefully. And so I think that kind of analysis that physics is very, very good at, finding patterns that are universal, finding simplified models that give you some insight and things like that, might very well be useful in the study of political science or economics or whatever. And there will be circumstances in which that is not the right way to analyze the situation. So I think that I can't tell ahead of time what will end up being the biggest contribution of physics to the human sciences, but I'm hopeful/optimistic that such a contribution will be found. James Farina says, I have a daughter considering a career in anthropology. How did you decide to become a scientist? Were any members of your family scientists? Did you always believe that you had the ability to become a world-class scientist? I started young in my scientific aspirations in elementary school. No members of my family were scientists or anywhere close to it, so I had no guidance either from family members or from school teachers or anything like that. I would just read books and hope for the best. So, I mean, maybe that's good and bad, because the idea of wondering whether I had the ability to become a world-class scientist never entered my mind. I just wanted to be a scientist. So the idea that there was a competition and not that many people got to do it professionally wasn't something that I knew enough to worry about at the time. And I thought that I would have no trouble getting into college, etc. I didn't know whether I would get into the best colleges. I didn't even get to apply because we couldn't afford it. Those anxieties about whether or not I was good enough to be at the world-class level didn't come in until I started thinking about graduate school. And then, then you're just always bombarded by the message that this is tough and you may or may not make it. And that's just what life is like in between the vast gulf of entering grad school and eventually getting tenured as a professor. But what I tell people always about the ability thing is you can't worry about it too much, because number one, there are probabilities involved, right? It's not like you can meet someone and say, oh, yes, you are able to do it, and someone else, oh, you are not, right? It's just not like that. It depends on so many completely unpredictable things, not just intrinsic features of the person. I've had many people I've known, many students, struggle at first, and then a light bulb goes off and they really get it and they become great scientists. And likewise, I've had students I've known students who have been really, really talented and yet never quite did it, never quite got into the whole actually being a scientist thing. There's a big difference between doing well on tests as a young person and being a professional scientist. Therefore, if you love it and you are willing to take the risk, just do it. Don't worry about whether you have the ability or not. Just see what happens. Learn. The worst thing that can happen is you learn some science and you put it to use in some other career. That doesn't seem like such a bad outcome to me. Anonymous says, does the math of physics want time to have a different sign than space? Would something break if you tried to write it down a Hamiltonian in a space-time with the metric signature plus 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 plus? So this is referring to the idea that in relativity theory, you can think about the difference between space and time in terms of the metric, okay? The metric is the way that you tell distances along curves in any geometrical construction, any manifold. A metric is just a distance measure. And in space, the nice thing about the distances along a curve in space is that whether you move along X or Y or Z, all of those motions add to the total distance of the curve. In space-time, it's not like that. There's a sign ambiguity that you can choose whichever way you want, but if you choose it so that paths in space have a length that adds up as you go X, Y, or Z, then going in the time direction, actually subtracts from your space-time interval, the length of the space-time curve. That's why going at the speed of light, which in relativity is morally equivalent to going an equal amount of space and time, has zero interval elapsed, and that's why a photon, for example, experiences no passage of time, because for particles that move on time-like or space-like paths, time-like or null paths, you can think of the total interval that they traverse as giving you the time that they experience. Anyway, all this is saying that this question is asking, could we imagine physics working in a world where all directions of space-time were equivalent, where it was plus, 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 plus. That is what we call a Euclidean signature to the metric rather than a Lorentzian one that we have in ordinary space-time. So you can definitely imagine physics working in that kind of construction. In fact, as a matter of practical reality, in quantum field theory, we very, very often imagine that we're in a Euclidean metric spacetime. We do calculations there and then say, okay, that implies a certain answer back in the real world. So as a mathematical trick, it is very, very useful in quantum field theory to imagine that we have a space world rather than a time space world for the 4 dimensions that we have. Now, that's a different strategy than the Hamiltonian that you're talking about here. Again, for people who don't know what a Hamiltonian is, number one, buy my book, The Biggest Ideas in the Universe, coming out September 20th. We'll tell you what a Hamiltonian is. But it's a way of thinking about the laws of physics that really intrinsically imagines that space-time is sliced into moments of time. Okay, the Hamiltonian tells you how you move forward in time. So there would still be ways to do physics if all directions of space-time were space-like rather than time-like, but you probably wouldn't use the Hamiltonian formalism for doing it. That's my guess. I can only say probably because you never know whether people are very, very clever and come up with something which is a Euclidean Hamiltonian formalism, but I don't know of any such thing. Murray Cantor asks a priority question. So remember that priority questions are questions where if you label your question priority question, for those Patreon supporters asking the questions, I guarantee I will answer it. I will try to answer it. I do not guarantee you will be satisfied with the answer, but I will give it a good shot. And the trick, the catch is that you only get to ask one priority question in your life. Now, I'm not really keeping track here, so it's the honor system, okay? Don't ask more than one priority question. There's an interesting question. I'm sorry, Murray, that I'm delaying your answer, but it will eventually come. I wonder about the game theory of this, right? A lot of people ask priority questions right away, but I would think, at least if I'm just a completely self-interested person doing the game theory of it, what I would first try to do is ask the question not labeling it a priority question, and then maybe I will answer it. I'm using the pronoun I in different senses there, but I hope you knew what it meant. If I were the asker, I would ask the question and see whether the podcaster, me, would answer it without labeling it priority. So then you save your priority question for later. And if it doesn't get answered, then you can label it priority, right? As far as I can tell, no one does that. Maybe that's just because you're all too good-hearted. Maybe it's because you're not all very good game theorists. I'm not quite sure what the answer is. Anyway, Murray's question is, I pride myself on being a good Bayesian, and I apply Bayesian nets professionally. However, a philosophical issue has occurred to me. A good Bayesian updates beliefs based on evidence. Doesn't that require that the Bayesian has to be 100% confident in the evidence? I suppose there are extensions of Bayesian theorems to account for this, but then you need additional evidence to believe the initial evidence, and so on. Have you seen any discussions on how to address this problem? I haven't seen discussions on how to address that problem specifically, but of course it is a problem, but I think that you don't need to go outside the Bayesian paradigm to address this. What you do have to do is just be honest about all of the quantities appearing in Bayes' theorem. So Bayes' theorem says you have a prior probability for some theory or some proposition to be true, and then to get the posterior probability, that is to say, the probability that this proposition is true conditionalized on the new data that came in, you multiply that prior by the likelihood that that data would be coming in if your proposition were true, and then you normalize it. So what I think is going on in your question is you have to be very, very accurate and honest about those likelihood functions, the probability of the data given the theory. So let's say that you are, asking about faster than light propagation of neutrinos, for example. And you do an experiment and you see the neutrinos are moving faster than the speed of light. Okay, so, if your two theories are neutrinos do move faster than the speed of light or neutrinos do not move faster than the speed of light, and you measure them to move faster than the speed of light, naively, you would say, aha, with 100% confidence, I now know that my theory that they do move faster than the speed of light was the correct one, right? No, that is clearly wrong because you've forgotten that you might have made a mistake. And that's very, very important. So when you do your likelihood function, what is the probability that you get this data given the theory? You have to take into account the fact that your data collecting procedure or your data interpreting procedure might be wrong, right? So when Murray says, doesn't that require the Bayesian has to be 100% confident in the evidence? I would say no. It requires that the Bayesian needs to be very, very accurate and honest about the probability of thinking they've gotten that evidence if the theory was correct. Now, how do you do that? I think that's the deeper question lurking here. And as you say, as you imply, there's no real algorithm for doing that, right? This is where judgment calls come in. Bayes' theorem is a theorem. It's a true fact about how you should update probabilities based on new information if you know everything perfectly. But you don't know everything perfectly. So putting Bayes' theorem to work in the real world requires those little bit of judgment calls. Bruno Teixeira says, you asked Ari Kirschenbaum if aliens would be dangerous, and he said something like, no, because colonialism is a human thing. But I thought his hypothesis would lead him to the opposite conclusion. Assuming our colonialism comes from natural selection, wouldn't aliens also be colonialist? And what is your take on this? So I didn't remember that part of the conversation precisely. So I actually went back and looked because I was curious. And I think that Arik is not saying that colonialism, or not even colonialism, but sort of, he used the word colonialism, but he was referring to as just sort of exploitation of other planets and whatever. He wasn't saying that it was an intrinsically human thing. He said it was an intrinsically located on one planet thing. So he wasn't making a statement about the intrinsic natures or goals of different species, us versus them. He was just saying it's impractical to be an interplanetary colonialist because the planets are very far away, and I think this is even true within the solar system. You don't need to even imagine going to other places, but it's really, really hard to get resources from other planets, right? It's very hard to get resources from our planet in particularly remote and dangerous locations. So to get resources from, Mars or Saturn or whatever is very, very hard. And to get resources from literally planets around other stars is exponentially harder. So I think that's all that Arik was saying. Now, that's not to say that I agree with him. I think that the point he was trying to make was, in his judgment, it's just not going to be practical to be colonialist in the usual sense when the purported colonies are at interstellar distances from us. That may or may not be true. I'm not actually sure about this. I think it depends on a lot of details we don't know about what interstellar travel will eventually be like. But I think that's why he wasn't trying to draw a distinction between human nature and alien nature in that sense. A. Lama says, when measuring the quantum spin of entangled particles, how are the axes defined? When Bob takes his particle to another galaxy, how does he determine his orientation? So what's going on in the background here is the idea of, some kind of EPR experiment. Einstein, Podolsky, and Rosen said, imagine that you have two particles that are entangled. They were actually, by the way, Einstein, Podolsky, and Rosen dealt with momentum and position. They were not dealing with spin. But later, I think it might have been John Bell, who said it's much easier if you just think about spins. Anyway, you could create a state of two particles where they're entangled. Let's say they are anti-aligned. They could also be entangled by being aligned, but anti-aligned in the sense that if one is spin up, the other is spin down, and vice versa, okay? Then to measure the spins, you need to set up a Stern-Gerlach experiment or some other kind of experimental apparatus that is measuring the spin along a well-defined axis. And what the questioner correctly asks is, how do you define that axis if you're not even on the same planet, if you're very, very far away? Well, there's two levels of answer to this. One is if you're not that far away, and we can be careful about what it means to not be that far away, you can just do something like bring a gyroscope with you, right? You can actually keep track of what the axes are between your starting point and your ending point, either by carrying some physical device with conserved angular momentum, like a gyroscope, or a gyroscope that you don't push on in any preferred direction, Or maybe you just set up some visual monitoring system, right? You're literally looking at it in some technologically advanced way, just doing the equivalent of what you would do if you were literally in the same room. Now, once you get far enough away, general relativity, the fact that space-time is curved, becomes relevant, and it becomes harder to uniquely define what you mean by pointing in the same orientation. It's still possible because, after all, if you take a gyroscope or something like that, and if it sort of in curved space-time, its axis tilts with respect to some coordinate system, well, the same thing would happen for your entangled particle, right? The spinning particle is itself kind of like a little gyroscope, so you should be in good shape. But by the way, when Bob actually takes his particle to another galaxy, no one cares that it's in another galaxy. It's just a thought experiment trying to drive home the fact that the existence of that entanglement does not go away, nor as a function of distance, nor does the fact that if you measure one, you instantly know the outcome that you would get measuring the other one. Alejandro del Rincon says, in general, public schools are better in rich neighborhoods and worse in poor neighborhoods. How is this fair? And what would you do to address this issue? Doesn't this only help perpetuate social inequality? Yeah, it does. I think this is completely true and is just kind of inarguably evidence that, at least here in the United States, which is the only place that I really am intimately familiar with, we don't care that much about inequality in that sense. I mean, to me, I've complained about this. I blogged about this, and I'm not an expert, so you shouldn't take my musings too literally as policy prescriptions. But it does seem to me intrinsically incredibly unfair that people who happen to be born in poor neighborhoods don't get the same kind of education that people who happen to be born in rich neighborhoods get. Even the most meritocratic libertarian who thinks that people get what they deserve, babies deserve all the same thing, right? But they don't get all the same thing. And so I think this is wildly unfair. And I think that we should have a system in the United States where, as far as public schools are concerned, roughly speaking, every public school student should have the same amount of money spent on them in their school system. And the way that it happens in the U.S., I don't know where you're from or what you know about the system, but it's mostly public schools in the U.S. are funded through a split of local revenues and state revenues. There's a little bit of federal money that comes through, but not very much at all. And often it's mostly local. Sometimes it's mostly state. It depends on the specific neighborhoods and things like that. And the local revenues are property taxes. They're not income taxes. They're taxes on the value of the property that you own, if you're a homeowner or a landlord or whatever, which is sort of like the maximally unequal way to do things. The more property you own, the more taxes you pay, the better your schools are. And that just seems wildly wrong to me. I see no justification for that whatsoever, other than the fact that rich people want their kids to get good educations, and rich people make the rules in some sense. So I think that would be a very easy way. It wouldn't be easy because there's a lot that goes into school quality other than amount of money that is spent per student, et cetera. But it does seem a very obvious source of inequity to me. So I have no better answer to give you than that. Jim Watson says, can gravity waves give us insights into the space-time between the source and us? Properties of gravity waves seem to be associated with the source, like the black hole merger, but are they affected by their travel to us, like losing energy or polarizing or whatever? Yeah, sure, absolutely. Losing energy is not a big thing because, there's not a lot of absorption of gravitational radiation. There's not a lot of gravitationally opaque things in the universe. And by not a lot, I mean essentially none, okay? Because there are not charges in the universe that can be easily pushed around. Eventually it would happen, like it's an approximation what I'm saying. If you had many masses that the gravitational waves were passing through, they would push those masses around and thereby they would lose energy eventually. But as a practical matter, that's a completely negligible effect. Polarization could be affected by the curvature of space-time and things like that, but not very much. However, I think the reason you don't hear about this so much is because it's just much harder to detect gravitational waves than it is to detect electromagnetic waves. As you know, you recently won the Nobel Prize. Not I, Kip Thorne, former Mindscape podcast guest, recently won the Nobel Prize for helping to do that. And therefore, if there's anything you want to know about space-time between here and there, it's just much better, more precise, more easy to get detailed information if you look at the light waves, the E&M waves coming from the source rather than the gravity waves. Okay, now I'm going to combine two questions together. One is from Michael Lacey, who says that I, Sean, tweeted the following, quote, AI is nowhere close to being conscious or self-aware, but it's getting pretty good at faking it and will get even better very quickly. That would be transformative, although in different ways than honest AGI would be, unquote. So Michael is asking, how will we know when honest AGI has been achieved? AI that's very good at faking it can pass the Turing test, since that's designed to detect human-like behavior rather than actual intelligence or self-awareness. Will we ever be able to distinguish between sophisticated AI and self-aware AGI without developing equations to define consciousness as an emergent phenomenon? And then Joy Kolbeck says, so it turns out that Russian chess robots are not only plenty strong enough to break children's fingers, but will do it too just because the child violated the usual procedure, taking his move too quickly. Do you think we are ready to accept/trust robot helpers in our homes anytime soon? So these are, I may or may not be doing the right thing by grouping these two questions together, but I think of them as flip sides of the same coin. Michael is saying, okay, given that AI is pretty good at faking it, how will we ever know when we actually do achieve consciousness in artificial intelligence? And Joy is saying, given that AI is not conscious, is not beholden to rules of common sense and morality that human beings are, when are we able to accept or trust it? To Joy's question first, I think is the easier one. Do you think we're ready to accept or trust robot helpers in our homes anytime soon? Yes. Clearly, empirically, we are. If you have a Roomba in your house, you are in some sense willing to accept and trust robot helpers. It's just a very low capacity kind of robot. It's not able to break your fingers. There's no hard and fast line between robots and other kinds of technology, right? Almost all technology, certainly cars or microwave ovens or whatever, have a lot of computer programming in them, as well as a lot of moving parts, and have both dangers and benefits. And we very happily put up with them. And so the point of my tweet that Michael referred to is that AI will, in some sense, become more and more ubiquitous. The ability to act human-like, if you take that to be what we mean by AI in this sense, that it's going to be there. So, if Joy, if you're saying, are we going to accept it? I think yes is clearly the answer. Should we be? Well, I think it's okay, but I do think we need to understand and be cognizant of the dangers. I think the story that everyone probably knows is about the Russian chess robot that literally moves pieces around, but it thought that the child it was playing against was cheating, and so it reached out and broke the child's finger, which is obviously just bad design on the part of that particular robot. But there's lots of things that can be badly designed, even if they're not AI. So I don't think that's a problem unique to artificial intelligence. To Michael's question, the clear answer is that I don't know, okay, when honest AGI will be achieved, and I don't even know if it's knowable. But what I want to, the point, I'll just reiterate sort of the deeper thought behind the tweet, which is that it's way easier to fake being human than to be human, okay? And I think that therefore the worries about super intelligent AI are perhaps not the most immediate worries we should be worried about. There's other worries. Not that I'm downplaying the potential threats of super intelligent, vastly powerful AIs. Sure, that's a worry. What I do worry about much more short-term and obviously are programs that will fool people into thinking that they're human, even though they're not. That opens up a whole new can of worms that we haven't thought about that much. So it's a instance of the fact that our imaginations are highly non-uniform. We're very easily able to imagine things that are like things we experience, but with a slight tweak somehow, right? So perversely, it's easier for us to imagine robots or AIs that behave humanly than it is the vast spectrum of behaviors in between completely non-human and human behaviors, right? So I think there's just a lot of phase space, a lot of design space open for human, quasi-human-like behaviors on the part of AIs that have not even a semblance of actual intelligence or common sense or values behind them. I think that's a much more short-term important issue than superintelligence or AGI or anything like that. Brendan asks, I'm curious how Ariel and Caliban managed to travel cross-country. Did you end up flying or driving them? We flew them, and I cannot imagine driving from one coast of the United States to the other with two cats, with, cat box and food and all that kind of worry together. So we flew, and it was interesting because, they're brother and sister and they've grown up together. They'd never been apart, but their personalities are different, and they have sort of different levels of courage in different circumstances. If you're vacuuming, Caliban is the biggest fraidy cat in the world. He will hide behind some big object and he will not come out if that vacuum is going. Whereas Ariel will stand up to the vacuum cleaner. And in some sense, she's a little bit more territorial. She'll protect her ground more than Caliban will. It's the opposite when they are traveling. Caliban took it like a champ. Once we got them into the cat carriers, it is a traumatic thing. They have no idea what's going on. They knew that for the past couple days there were noises and weird things going on in their house because the movers were there, etc. So they were already a little bit freaked out. And Caliban, I don't want to project onto him, but he seemed to kind of like it. He was like looking around and, he was ready to, say hi to people and didn't raise a fuss when we were actually in the plane. And very soon after getting to the apartment in Baltimore, he was walking around and, looking at his new home and figuring out what spaces were going to be his, where the sunbeams were, etc. Ariel did not take it well at all. She was frightened the whole time. We did everything we could to reassure her, but she was just not happy. And it's taken her a while to sort of crawl out from her, dark, comfortable places, even in the new house in Baltimore. She's finally doing it now. She is adjusting. The great thing about cats is short-term memories. They do not really linger on in their worries. So she's adapting fine now. But yeah, I could imagine, honestly, if we only had Caliban, I could imagine he could be a traveling cat. Ariel, there's no chance that she would ever be a traveling cat. Kathy Seeger says, no proper question this time around, but I'd be happy if you could recommend a book, a fiction book. Think of a book you really loved, no matter what genre. Thank you. So I always, I hesitate at these kinds of questions. I have some, standard answers to give, but I'm very well aware that different kinds of people like different kinds of books. I'm not a moral objectivist or an aesthetic objectivist either. I don't think that there's such a thing as the best books that everyone should read. So my standard answer, if you, force me to say what is my favorite book of all time, Pride and Prejudice by Jane Austen. I just love reading that book, read it over and over again. And it's clearly, it's not science fiction-y or anything like that, but Austen was just better than anyone I've ever read at getting all of the little details of human thought exactly right, okay? And that doesn't mean it's for everybody. Like, if you are into it, if you get it, it is one of the funniest books you'll ever read. It's a page turner, and it's quite moving in places, and the characters are just lovable and hilarious. But if you don't get, for example, the fact that Jane Austen very, very often speaks in, even though it's not first-person narration, she very often speaks in the voice that one of her characters would use, okay? So she's speaking in the kind of thought process that would belong to one of the characters, not to her, the author. And even sometimes she's speaking sort of in the voice of conventional wisdom, even though she doesn't believe in the conventional wisdom. So there's an enormous amount of sarcasm and facetiousness and mockery going on, teasing in Jane Austen. And sometimes people read it literally and don't get it, and they think this is horrible. And, likewise, if it's slow moving in terms of action scenes, if you want to see a lot of chase scenes, then Pride and Prejudice is not the thing to read. Two more books that I name drop in these circumstances. One is The Moon is a Harsh Mistress by Robert Heinlein, science fiction book about a revolution on the moon that was my favorite book as a kid growing up when I was reading all the science fiction stuff. I recently reread it and I claim that it holds up 100%. Still love that book. It's just rich, fully imagined, and very, very easy to read. It's written in a sort of dialect that he made up. So that's a tiny, tiny barrier to entry right at the start, but there's no real difficulty reading it. And the other one is Mason and Dixon by Thomas Pynchon. Thomas Pynchon, famously a living American writer who is one of the leader of postmodern literature in the 60s, 70s, 80s, etc. Mason and Dixon is my favorite book by him. It's also written in a very thick dialect that does require an enormous amount of effort. So compared to the other two books, Mason and Dixon requires an enormous amount of commitment on the part of the reader, but it totally pays off. It is, again, so well done, so rich, so hilarious, both intellectually stimulating and kind of goofy and silly and crazy at times. And like all Pynchon works, it's sometimes hard to know who's talking, which scene this is in, where we are, why we're doing it. You got to sort of live through that, push through, and I think that the reward is absolutely there. Gravity's Rainbow is, of course, Pynchon's most famous book, and that is sort of all of the difficulties of Mason and Dixon with the difficult language, the difficulty of knowing where you are and what's going on, are amplified by a lot in Gravity's Rainbow. And I think that Gravity's Rainbow is actually one of his earlier works, and he was a little bit less good at the human side of things. It was a little bit overly intellectualized, and there's some very, very human moments there in Gravity's Rainbow, but the characters are just much more alive and personable and interesting to me in Mason and Dixon than they were in Gravity's Rainbow. Okay, I'm going to group another two questions together. One is from Eric Dovigi, who says, how did Einstein go from having an intuition about the nature of space and time to actually getting his pencil out and figuring out those field equations? In other words, can you talk about the methodology of theoretical physicists? And Sean Herbison says, what does a theoretical physicist actually do on a day-to-day basis to work on physics? I know there are a lot of other things you do, teaching, getting grants and such, but what does the actual physics work look like? Broadly speaking, I'm assuming it involves at least research and some form of equation crunching, but I'm curious to get a better picture. So obviously the difference between these two questions is one involves me and the other one involves Albert Einstein, which is probably a very large difference. But nevertheless, there are similarities when it comes to how theoretical physics gets done. I mean, we can talk about Einstein first, but it isn't necessarily a representative sample because, it's Einstein. But Einstein was obviously extraordinarily smart. Don't need to tell you that. He was not the world's best mathematician. He was really, really good at math, don't get me wrong, but it wasn't his specialty. What he was really a genius at was this kind of thought experiment analysis, figuring out what was important, what was not, as we already talked about. So it came to the point in the early 20th century where he had figured out special relativity. Basically, many other people had put together pieces of special relativity, and Einstein's main accomplishment, if anything, was just to say, you don't need this stuff called the ether anymore. You can just change your notions of space and time and get all the right answers out. What he didn't do at the time, 1905, was to say that space and time should be married together to make space-time. That came 2 years later by Hermann Minkowski, who was one of Einstein's old professors and who was a mathematician. And he had this elegant way of thinking about special relativity in terms of space-time, which we now call Minkowski's space-time. And Einstein actually didn't like it. He thought it was just showing off mathematically, a little bit too complicated, and who needs that? We're all physicists, right? But he was, of course, thinking about this question of gravity, because once you have special relativity, once you have this new view of space and time, it's kind of like when you have quantum mechanics and you have to go back and all of your classical theories need to be updated to become quantum theories. When you have relativity, you have to go back and all of your Newtonian theories have to be made relativistic. Happily, electromagnetism was already relativistic. Electromagnetism was the inspiration for relativity, but Newtonian gravity was different. So fitting gravity into special relativity was an obvious thing to think about. And it was the principle of equivalence that really got him going, which was exactly his sort of thought experiment genius, where he realized that if you didn't know that you were in a gravitational field, you couldn't necessarily tell the difference between, let's say, being in a house on Earth with no windows versus being in a spaceship that was accelerating at 1g. And that means that gravity is universal. And that means that gravity, if you're Einstein, it means that gravity is a feature of space-time itself. And he thought about that a lot, and he actually, I'm not exactly sure how it happened, but he came up with the idea that maybe the curvature of space-time, the geometry of space-time, could be what was going on. He didn't know anything about what at that point was the modern view of geometry, okay? That's something that was a specific thing that mathematicians knew about, that had been invented by Gauss and Riemann and their successors in the last half of the 19th century. So Einstein sort of got the idea that maybe he should catch up. And he talked to friends of his. Marcel Grossmann, in particular, was a good friend of his who knew all this fancy Riemannian geometry stuff. And so he learned it. So what was involved in Einstein inventing general relativity? Reading books and papers about Riemannian geometry was a big part of it. So first getting the idea that you needed to know Riemannian geometry, then learning it, and then asking yourself the physics question, okay, if this is the math behind understanding curved space-time, how can I turn it into physics? So how can I use the mathematical quantities that are defined by Riemann, etc., and relate them to physical quantities like planets moving around the sun in orbits and stuff like that. So you need to have the equivalent of mass, right? Because mass is the source of gravity in Newtonian physics. So Einstein had to figure out that there would be a tensor, which we now call the energy momentum tensor or the stress energy tensor, that would replace the idea of mass. And he had to relate that tensor to something involving the curvature of space-time. And there's a lot of trial and error, honestly. He guessed, he pushed around symbols. He said, what could fit with what? He was still brand new at it, so he hadn't quite absorbed all of the intuition and tricks of Riemannian geometry, but he eventually got there. So a lot of it, I think, besides the studying other people's stuff, a lot of it is just pencil and paper. You're scribbling equations, you're drawing little doodles, you're asking yourself what should fit together. The math is crystal clear, but turning into physics is hard. And so for Sean Herbison, it's not that different. Even if you're a modern theoretical physicist, if you're a pencil and paper physicist like myself, okay? So many physicists, of course, these days use computers to simulate things, but there's still a lot of us who are sitting at our pads, either iPads or pads of paper, and scribbling equations, scribbling at the board. Some of it is exactly, all of it is exactly like what Einstein did in some sense, because remember, I mentioned Marcel Grossmann, who was Einstein's friend and also tutor in Riemannian geometry. So talking to other people is an important thing. There's a great story that I actually mention in The Biggest Ideas in the Universe, coming out in a short time, because I talk about Einstein's equation. I derive Einstein's equation in some sense for you. And so I discuss what all the symbols mean and so forth. And, everyone knew each other. Like everyone knew that Einstein was thinking about gravity. He had made proposals along the way. You write papers updating people on your progress. And so he talked to people. And in fact, David Hilbert, the famous mathematician, invited Einstein to go give a series of lectures at Göttingen, where Hilbert was professor, which Einstein did. And Einstein literally stayed at Hilbert's house. And guess what? They talked about math and physics all the time. And as a result, Hilbert was inspired to think about gravity and curved spacetime. And he came up with a different way to derive what we now know as Einstein's equation. And it worked really well. In fact, we call it the Einstein-Hilbert action. He used the action principle, the principle of least action, to derive Einstein's same field equations. So talking to people, standing at the board, scribbling equations, sitting by yourself, scribbling equations, trying to fit together the math and the physics. There is a balance between asking the right question and coming up with the techniques to answer that question, right? And how you do this in either case is kind of mysterious. I guess the last thing I will say is I did write a series of blog posts on the evolution of a paper. This was several years ago, but one of the first papers that I wrote after coming to Caltech was with a graduate student at the time, Lottie Ackerman, and Mark Wise, my colleague there. And I explained in a series of 3 blog posts how precisely that paper came to be written. And that gives you, if you want to look at that, it'll give you a picture of how theoretical physics gets done. It started with an idea that Lottie had. She just had a question, what would happen if inflation happened at different speeds in different directions in the early universe? And she asked Mark about it, and Mark was like, oh yeah, we could probably calculate some predictable, observable consequences of this in the microwave background. And then they brought me in, and I said, yeah, in fact, there's this kind of energy source that would make that happen. And there's also, these tricks to doing the CMB calculations. So the 3 of us collaborated and put that together, if you want to check that out. Qubit says, there are quite a few times when you mention that classical mechanics is just a limit of quantum mechanics. I wonder how settled this debate is. What about the spread of a free object in space that the Schrödinger equation predicts, but is not seen in our everyday life? Seems like we need many worlds in order to explain this, and it must therefore be highly controversial. Well, we don't need many worlds to explain the classical limit of quantum mechanics. Whenever you're tempted to say, we need many worlds to explain something, what you really should be asking is, are there other models that also explain it? And in this case, sure, there are other models of quantum mechanics that also have the classical limit just as well. But you are correct in putting your finger on something tricky and slippery about the classical limit of quantum mechanics. It doesn't seem robust in some sense, and this is what Schrödinger himself struggled with. He was hoping that his equation for the wave function would describe a wave that kind of bundled up and came together and looked particle-like, a wave packet. But it doesn't. It does the opposite. A free particle in the Schrödinger picture will spread out all over the universe. So why doesn't the universe quickly become non-classical and look very quantum? Well, there's at least 2 things going on. One is that when the degrees of freedom that we're talking about, whatever that is. So maybe you're talking about the Earth, okay? The Earth has a center of mass, and you can talk about its quantum mechanical evolution of the center of mass of the Earth. But when those degrees of freedom become very, very massive, like the Earth, then you can show that the rate at which the wave function spreads out is much, much smaller, okay? Heavy objects act more naturally classical than light ones do. And the things that we come across in our everyday classical lives are generally very, very heavy. Their wave packet spreading is not very noticeable. That's the easy part, and that part is traditionally taught in quantum mechanics courses. The hard part is you also need to talk about decoherence. You need to talk about why wave packets are concentrated in the first place, and that is a subtle question having to do with pointer states and decoherence and complicated things like that. And there, I think, honestly, I don't think the story is settled yet. There's been heroic work done by people like Wojciech Zurek and others on the emergence of classicality and why certain states show up in the world. But I think that there's still a little bit of work remaining to be done before everyone agrees on precisely the right story to tell. Ronald Buck says, 10-second question. Other than attending a book signing, is there any way to get an autographed copy? Short answer, no. I mean, people do ask this, but there just isn't a way. And I keep thinking that maybe we should get there to be a way. But I don't want that way to involve me taking a book and packing it up and taking it to the post office. So maybe you should be asking the publisher rather than me. If the publisher wants to set up some way that I sign 100 books and they sell them at some different rate, that would be fine with me, or some bookstore or something like that. But there's no system right now in place for that. Dan Pye says, I recently read Sam Harris's The Moral Landscape, and it occurred to me that there seems to be very little practical difference between his moral objectivism and your moral constructivism, despite the radical ontological differences. Both postulate that there are correct answers to moral questions that reason can help us discover and to persuade others to accept. Do you find value in Harris's approach to morality despite the argument's central is-ought problem? Well, I think that you're right that there are 2 different questions to ask. One is sort of ethical and one is meta-ethical, okay? So the ethical questions are, what do you actually think are the rules, are right and wrong, are principles of moral behavior? The meta-ethical question is, how can we justify those principles? Why do we think that these certain principles are the right ones to choose? And the obvious difference between Sam Harris and myself is on the meta-ethical level. I think that the arguments that he puts forward to go from to do the science of morality, as he and other people have called it, are extremely unconvincing to me. Now, we might very well end up in the same ethical places. I actually don't know. I don't know what Sam would put forward. I'm not even sure what my own ethical principles are, so it's impossible for me to say that someone else has the same ethical principles as myself. But I think that the meta-ethical question is really important here. It's certainly not surprising to me that someone can be a moral objectivist and come up with the same exact ethical principles as a moral constructivist, because from the moral constructivist's point of view, there are no objective moral rules, right? There are just our moral intuitions, and we sort of say, as a matter of agreement, let's behave this way. And sometimes we disagree, and then we throw people in jail or we get in fights or whatever. And again, as I like to say, guess what? This is exactly what happens in the world, so you shouldn't be surprised. Whereas to us, the moral objectivist is incorrect, but they're coming up with some justification because they also have moral intuitions, right? I've never met a moral objectivist who used logic and reason to come up with moral principles that were wildly at variance with what they wanted the moral principles to be, right? I don't know of anyone who said like, well, I really think that doing X is bad. I don't like it. It repulses me, but I've used logic to say that it is the right thing, and therefore that is how I will act. Generally, moral objectivists end up justifying their moral intuitions just like constructivists do. They just don't admit it. Now, I realize that is a highly biased way of putting it, but I'm just letting you know what my feelings are. I'm not surprised when moral objectivists and moral constructivists tend to agree, but I do think that it's important and it matters how you justify these things because there are gray areas. There are perfectly legitimate questions to which the answers are not clear. And when that's the case, how you justify your moral principles is more than just a matter of convenience. It can really make a difference because we don't all come into life or even develop into people who have crystal clear, perfectly sensible, consistent, coherent moral systems. The development of those systems is an ongoing process, and the justification for it matters. Ratboy.exec says, is there a possibility that the Everettian and cosmological multiverses are actually the same thing? Meaning, could it be that when we conduct a quantum experiment, there's a proportion of places in the universe in which the experiment goes one way, a proportion in which it goes the other, and the apparent collapse of the wave function is really us finding out which of those kinds of places we're in? It's possible. There are things like that are true. So that are on the table as maybe being true. Let me put it that way. So, but let's distinguish. There is absolutely a conceptual difference between the Everettian and cosmological multiverse. They're different kinds of things, deep down. It is possible that in practice they work out to be similar kinds of things, but also maybe not. There's no necessary connection between them. So the Everettian multiverse happens in one location when I am doing one experiment, one observation of a quantum system that's in a superposition. I measure it, and different outcomes lead to different universes becoming real. There's nothing there about different locations in space, far away, et cetera, et cetera. Whereas the cosmological multiverse is exactly about different locations in space, far away, different things happening. The cosmological multiverse, there's no necessary thing that there is repetition, okay? Just because there's me here in this room that I'm in Santa Fe recording an AMA, the cosmological multiverse, even if it's infinite, does not imply there's another copy of me or many copies of me similar to me far away. Maybe the laws of physics are just very different in every one of those infinitely many other universes, okay? So conceptually, they're very different things. There was a proposal several years ago, one paper by Yasunori Nomura, another by Lenny Susskind and Raphael Busso, both of them pointing out that there is a version of complementarity, horizon complementarity. This is an idea that Susskind and others had in the context of black holes that said that If you think about what a black hole is, your description of what the black hole is different for observers who are falling into the black hole versus looking at it from outside, okay? So from the point of view outside, you think, according to this principle, that the black hole really is just like a membrane at the event horizon. There's a set of degrees of freedom scattered across the event horizon. You can count how many they are. That's where the entropy of the black hole comes from, et cetera, et cetera. And that's really what it is. And all of this stuff that you learned in a general relativity course about how there's nothing at the horizon, from the horizon complementarity point of view, that's what you would see if you were falling in, but it's not how you describe the black hole from far away. So it's a way of saying that really all that exists can be summed up from the point of view of an outside observer as living at the horizon of a black hole. Okay, so what does that have to do with the multiverse? If you apply that same idea, but inside out, to cosmology. You know, we live in a universe that is accelerating, so we're approaching a de Sitter universe kind of thing. That means we have a horizon around us, and we are at the center of that horizon. And what that might mean, maybe, who knows, this is just a speculation, we're not sure about any of this stuff. What it might mean is that to us, the entire outside world is equivalent to a set of degrees of freedom on our horizon around us cosmologically. And that means there's only a finite number of different things that can possibly, in principle, be happening in the outside world, because the entropy of the universe of the horizon around us is finite, okay? So that's very different than this classical picture where there's an infinite number of things that can happen far away. So you take that idea and you combine it with the idea that there are multiple vacuum states that we might be able to live in, right, in string theory or whatever. So multiple local laws of physics that you could temporarily have in the universe. And there are transitions between them via quantum tunneling. And quantum tunneling means branching of the wave function, right? Going from one quantum state to another one via tunneling. So the idea is that in this picture, the whole universe, the whole multiverse, is all contained within one horizon size of a single universe, but the quantum state inside that horizon is a superposition of different kinds of vacuum states. So in that sense, the whole multiverse is right here in some sense. That's a very loose sense, and it pains me even to say it because multiverses don't have locations like that. But the idea is that there's a connection between the Everettian and cosmological notion of multiverse in that picture, but no one knows whether that picture is right. Certainly, again, in principle, under different kinds of laws of physics, you don't need to have any necessary connection between these two ideas. Kevin says, do you have any opinions on working for a few years before applying for a PhD in physics versus applying for one immediately after graduating? Specifically, how do universities and professors view potential PhD candidates with continuous academic experience versus an interrupted one potentially in a job that isn't very relevant to physics either? I think the short answer is it's absolutely possible to do something in between undergrad and grad school other than just continuing on straight into it, but it does not help your chances. So if you think about applying to grad school as something that has a chance of success, you don't know, it's not 100%, it's not 0% either in any particular application process. You can't ever say that, this or that will prevent you from going to grad school or get you in or anything like that. It's all probabilities, okay? And my feeling roughly is that taking time away from academia lowers your probability of success. It does not make it zero. There's plenty of successful counterexamples to that, but it doesn't help either. The admissions committee for a physics department is not going to look at your resume or CV or whatever, your application, and say, oh yes, they spent 3 years doing computer programming or hiking across Europe. That's the kind of student we're looking for. I'm not making any moral judgments about whether they should say that, but they don't generally say that, okay? They like the idea that you are devoted to doing nothing but physics. That's what they like. Same thing for eventually getting tenure, right? They like the idea that their junior faculty members are devoted to doing nothing but physics research. That's what they like to see. And again, I'm not making any moral judgments about what they should like, But my advice, all else being equal, would be that lowers your chances. Does it lower your chances so much that you can't get in? Not necessarily. That depends on what else is going on your application. But that's the sign of the effect anyway. Vikintas Morvenas says, do you like fantasy books, movies, TV shows? And if so, are you considering meeting G.R.R. Martin there in Santa Fe? I do. In fact, I was a big fan of the Game of Thrones series up until the last season. No plans to meet G.R.R. Martin here in Santa Fe. He's not in Santa Fe right now, I don't think, because I think he was just in the news for going to San Diego Comic-Con and getting COVID there. So I hope he's okay. Hope G.R.R. Martin gets better very soon, because we all want to see those other books. Paul Hardy says, I read Lawrence Krauss's A Universe from Nothing. Not sure I'm understanding it. I'm not an expert, of course, but it seems as though instead of proving the universe actually sprung from no thing at all, he just changes the definition of nothing. I always wonder which is easier to accept. Stuff came from no thing at all, or stuff has always existed. So, I kind of am not that interested in debates about whether people change the definitions of things. I don't care what you choose the definition to be. Just tell me what the definition is, and then we can decide whether that's the question we're interested in. So it's certainly true that in books like that, they don't really explain why there is something rather than nothing. They don't even try. I mean, a lot of the impact there came from a misappropriation of a quote from Frank Wilczek, former Mindscape guest. Frank was working on baryogenesis, the matter-antimatter asymmetry. Why are there more particles in the universe than antiparticles? And he proposed a theory where a symmetric state with equal numbers of particles and antiparticles, which of course includes zero, would be unstable. And so the motto is, there's something rather than nothing because nothing is unstable. But what Frank had in mind about something and nothing is just matter particles in the universe versus no matter particles in the universe. But empty space without matter particles is not anyone's real idea of nothing. Or the quantum vacuum, or whatever you want to call it. That's not nothing, that's something. It's a quantum mechanical state, okay? So it's still an interesting question. I mean, and that's my point, is that what are the interesting questions and what are the answers to them, okay? So how did our universe start? How did it evolve into the state we see now? That's a very interesting question. I don't think there's any special insights into it in that book, but it's something that we don't really know the answer to and would like to know the answer to. It is, in my mind, a completely separate question from why the universe exists at all. And I think that the whole logic of the question is very, very different. I've written about it. If you Google why is there something rather than nothing, you can find my paper. And I tried to make the case that this is the kind of question that might just might not have an answer, okay? There is no such thing as the reason why the universe exists. That, I think, is the most straightforward answer. And is that satisfying or not? I don't know, but never promised you a rose garden. No reason why philosophical questions have to have satisfying answers. They just have to have true answers. Stephen Noble says, what's your belief on the existence of innate mathematical ability? Is some math just out of reach for most people, like how most people would never be able to slam dunk, or should we shrink differences in abilities with better education? Could we shrink differences in abilities? There's sort of three different questions here, and they have implications that I don't necessarily sign on to. So I think it's clear that innate mathematical ability exists. Look, I love my cats, but I have more innate mathematical ability than them. They're very darling, but they're not very good at solving differential equations. And there's no reason to think that the same thing shouldn't be true for human beings as well. I don't think that means that some math is just out of reach for most people. Maybe it's harder for some people than others, but I don't think there's any barrier, any phase transition that certain kinds of math are just out of reach for most people. I think that most people just don't try, or most people aren't educated effectively, or whatever, if they do get this opinion that they're not very good at math. I don't think that we're very good at sharing the joys of math widely. And that's one of the reasons why in the new book series, I do all the equations. And I'm sure many people aren't going to like it. They're not going to be interested in it. Whenever a new book comes out, you instantly get these one-paragraph reviews from Kirkus and from Publishers Weekly, right? And you're hoping to get a good review, and you have no idea. They're all anonymous reviews. And so the reviews are out for the biggest ideas in the universe, and the Kirkus reviewer really liked it, and the Publishers Weekly reviewer really didn't. And it's pretty clear the Publishers Weekly reviewer didn't even read the book. They just saw that there were a lot of equations and were like, I don't like that. And there are going to be people who are like that, okay, I absolutely know that. But for the people who maybe are a little bit curious, maybe they're willing to put a little bit of an effort. The goal of the book is not to force you to read equations, but to allow you to understand what these equations say if you want to. And I think that almost everybody can do it. That's why I wrote the book, because if you want to sit down and open your mind and think about it, I'm doing my best to let you understand the mathematics behind this. And I think that almost everyone can access it. Now, the final question, could we shrink differences in abilities with better education? We can certainly increase everybody's ability. Whether or not they will shrink or not, I don't know. The differences will shrink or not, I don't know. But I think that better education is certainly possible and important and could make everybody better at math. I'm all for that. Peter Blankenheim says, do you consider yourself strongly emergent, weakly emergent, a myth, or something else? So I do not consider myself a myth. I also do not consider myself strongly emergent, at least not from the elementary particles of which I'm made, because I don't think that there is any strong emergence from elementary particles. I think there's an interesting question about whether there can be strong. I think that the idea of strong emergence, which I've talked about it before, but if a particular person out there listening doesn't know, weak emergence is the idea that you can have some theory of little things, right? Atoms or molecules or whatever, and you can put them on a computer and find certain kinds of collective behavior, like solidity of a table or liquidity of water or something like that. No one thinks that this stuff is violating the fundamental laws of physics. It all follows from the localized reductionist interactions between the particles of which it's made. Strong emergence says that if you have a theory of tiny little pieces and you put that on a computer, there are things that will happen in nature that are not predicted, that are not compatible with that kind of explanation, that there's some new ingredient you need over and above the simple interactions of local pieces, atoms or particles or whatever, to explain the higher level emergent phenomena. So my view is that the existence or not of strong emergence depends on the two levels you're talking about. There's a micro or lower level, a macro or higher level. If the micro level has entirely local, extremely simple dynamics, like we do in particle physics and quantum field theory, then there's no room for strong emergence from it, unless you think that the micro level is just wrong, which I don't, okay? But if your micro level is like people, and your macro level is society, okay? That's a different kind of comparison between, people make up society. That's another possible case of emergence. People have interactions with each other that are not strictly local, and certainly people's internal states are not very simple, unlike electrons, okay? So there maybe I could see the possibility that there are things that happen in collective behavior of people that you can't quite capture in any particular simple theory of individual people interacting with each other one-on-one. Okay, I'm not sure that that's true. I'm just trying to be open-minded about it. I think that it's not as clear in that case as it is the absence of strong emergence in the atoms and particles case. So if you think about myself being emergent from atoms and particles, that would be weak emergence, not strong emergence. Sunis Mended says, given the very real possibility that the U.S. will cease to be a functioning democracy in the near future, what, if any, specific steps are you taking to prepare for what comes next? Have you thought about fleeing to a different country, beefed up emergency preparedness, etc.? Roughly speaking, no. I've not thought about any of those things. Look, even if, and I think I agree that there is a non-trivial chance that the U.S. will cease to be a functioning democracy. What does non-trivial mean in this case? I don't know. But it's enough that whereas 20 years ago, I would not have considered the possibility seriously, I think that right now you do have to consider the possibility seriously. But I think there's a big difference between not being a functioning democracy and riots on the streets and mobs burning down houses, okay? Those are not the same thing. There's plenty of monarchies where the actual day-to-day life is pretty simple and straightforward. Maybe you lack some freedom to get on the internet or say what you want, but you still, at a day-to-day level, live your life. So I'm very, cognizant of the possibility that that's what happens. Look, if the Republican Party manages to undermine the way that elections are held and decides that their state legislatures can just make up who they think the winner is, no matter what the actual voting outcome was, we will have effectively gotten rid of democracy in the United States. But I can imagine that for many people, life just goes on as usual. It would be worse for some people, but it would be kind of like, Republicans are in power. The real difference is they will never go out of power once that happens. And I think that would be terrible. But my immediate plan would be to stay here and fight it, not using guns and pitchforks, but using ideas and persuasion as much as I can to try to get people to appreciate that this is not how things should be. And maybe things, there's also the possibility that things are much more dramatically worse and more drastic steps will be taken. But I don't think that's the most likely outcome right here. Okay, now I'm going to group together a bunch of questions. You will see what the common topic is. Eric Stromqvist says, what outstanding questions in cosmology or astrophysics do you expect are likely to be answered by data from the Webb Space Telescope now that it has become operational? Andrew Goldstein says, is it possible that JWST's ability to see further back in time and with greater resolution could expand our understanding of quantum mechanics? Sheldon Silliman says, my question is about the potential of JWST to advance our knowledge of the quantum world. Will obtaining information about the relative chemical compositions of early galaxies provide new information relevant to the Big Bang or inflation models? And Sam Hartzog says, I was thrilled to see the first images from JWST that got me thinking about what might be in the realm of space telescopes 2 or 3 decades down the road. In spherical Cal units, there's 2 orders of magnitude between the maximum detectable wavelength of the JWST and the cosmic microwave background wavelength. How much juicy scientific goodness do you think we might wring out of the gap between the two? So first, a footnote. Sheldon Silliman asked a question last month, and I guessed that was a pseudonym, but it was not. So I honestly and sincerely apologize, Sheldon, for that. I mean, obviously, from some of the names I've read previously in this AMA, we do get pseudonyms here, and that's perfectly okay. But I shouldn't presume that someone's name is a pseudonym just because it could have been, and I'm sorry about that. I really do apologize. Sorry. But for these questions, let me give a sort of big picture answer because there's a lot of similarity here, and then I'll try to be a little bit more fine-grained. JWST is an amazing instrument that will teach us a lot about science. There are plenty of questions in science that are not questions of fundamental physics or the origin of the universe. JWST is not meant to tell us about the nature of quantum mechanics, the origin of the universe, what happened at the Big Bang, or anything like that. The 2 main science goals are the early galaxy formation history of the universe and exoplanets, planets around other stars, right? Like we talked about with John Johnson recently. Because JWST is an infrared telescope, which means, number 1, it can see sort of glowy light from planets and things like that. And number 2, it can see galaxies in their early formation period because the light from them is redshifted by a lot. So an infrared telescope is very helpful there. And of course, just the resolution of the telescope is enormously good. So the kind of astrophysics that we're learning about is well described by the standard model of particle physics and general relativity. There's almost no reason to think that we will learn about new fundamental physics from JWST. And that's okay. Most interesting physics is not fundamental physics. Most interesting physics is plenty compatible with the standard model and general relativity and quantum mechanics as we know it, okay? So it's still really, really interesting to think about how galaxies form, how stars form, how black holes form at the center of galaxies, how the planets are distributed around stars in our galaxy, what the nature of those planets are and their atmospheres. All these are really, really interesting questions. None of them have anything to do with quantum mechanics at a fundamental level or general relativity or anything like that. I mean, what I mean by that is, of course, quantum mechanics and general relativity are involved in them, but there's no real chance, you could always be surprised, but there's no real prospect that you're going to modify our understanding of quantum mechanics or general relativity on the basis of that. Likewise, for the Big Bang or inflation or whatever, there's much better ways to get information about what happened near the Big Bang than there is JWST, because telescopes like JWST have relatively narrow fields of view, right? You're trying to focus in on a galaxy or a cluster of galaxies or something like that. Most of the interesting information about inflation has to do with the spectrum of perturbations of density in the early universe, for which you want to look at the most universe that you possibly can. That's why things like WMAP and Planck do all sky surveys. It's sort of the complement of what something like JWST does. And for Sam's question about the gap in between JWST's wavelengths and the CMB, well, yeah, there's something called radio telescopes. They do that all the time. Wavelengths longer than infrared are get to be in the microwave and radio regime. And there's a really, really nice feature of that regime, namely that our atmosphere is largely transparent to it. So you can look at it without going into space. Our atmosphere absorbs infrared light, which is causing the greenhouse effect. You may have been locally affected by this fact very recently. That's why to see it, you have to put a telescope out there in space. But to see radio waves, you can just do it right here on Earth. Now, you can do it better and more precisely out in space, which is why WMAP and Planck were satellites, because if you want to do an all-sky survey at a very, very low temperature, it does help to go to space, okay? That's what the microwave background satellites do, but there's very, very effective microwave background observations going on here on Earth, at the South Pole, in Chile, and elsewhere. You can easily look at small patches of the CMB sky right here on Earth, no problem. Likewise, the Space Telescope, the Hubble Space Telescope, was looking at visible light, which does pass through the Earth, but it's more clear if you're out there in space. But if you're down here on Earth, there's still lots of very, very useful, interesting, visible wavelength astronomy going on, okay? So we're definitely looking in that gap using good old-fashioned radio telescopes. Sean Miller says, if biological systems maintain homeostasis by minimizing the delta between what's expected and what is perceived, and this delta is driven by probability distributions tied to vital interests, how is this biological computation different from computation that is maintaining homeostasis but is not tied to vital interests? To put it another way, what is the difference between biological perception and non-biological perception? Well, if I'm understanding this question correctly, it's an interesting issue, but it's somewhat philosophical. I think at the scientific/technical level, there's no difference between biological perception and non-biological perception. In both cases, you have detectors, in some sense, interacting with the rest of the world in a way that conveys information about the outside world to the system doing the detecting. The question is, what do you do with that information that you've detected, and what is the purpose for which you are detecting it? And just letting the word purpose seep into your discussion there is already tilting the scales a little bit, right? When do things have purposes? So I don't know if we talked about it. I think maybe we did, but the interview with Dan Dennett here on the podcast touched on a lot of interesting things. And one of Dan's big ideas is what he calls the intentional stance, which is when you assign intent, purposes, goals to a system. Okay. And his idea, and I'm not sure, I'm not an expert on this, but I'm just cluing you in on the idea if you want to read more about it and become an expert yourself. But the idea of someone like Dan is, look, people are physical systems, just like robots are, or computers, or other parts of the world. Sometimes it is useful and illuminating to talk about these physical systems as if they have intents. Intents in the I intend to do this or intend to do that. Not that they're intense about their intentions. I suppose I should say they have intentions. So we take a stance towards something that attributes to it goals, purposes, intentions whatsoever. Why? Well, because that gives us insight, because it's a useful description. It's like, why do we attribute temperature or pressure to a fluid, even though we could just talk about the individual molecules? Well, because it's a description that gives us information that is useful and can be made to make predictions. could be used to make predictions, etc. Likewise, if I say, oh, that person intends to shoot me, that has conveyed very interesting and important information that would be less usefully conveyed by just listing the state of all the neurons in their brains, okay? And if you think that that's what's going on, then you should be asking, well, when does it become useful to attach intentionality to physical systems that are not biological systems? And the answer is, I don't know. I mean, it could in principle be very complicated. I mean, there's the sort of meta-philosophical question, what is going on? Is there something that is an essence of intentionality or, biological desire to maintain homeostasis that is different at a deep ontological level than the fact that a thermostat maintains your house at the right temperature? And I think that Dan Dennett and I would say, no, there's no deep essential difference at the ontological level there. But you don't add anything to a discussion of a thermostat by saying, oh, it intends or it wants or it desires to keep your house at the right temperature. Whereas you do get some insight in talking about a complex system like a person in talking that way. So there will be some crossover from one to the other. It might be subtle and unclear when you do it. That's a good thing to talk about, but I think the underlying philosophical question is more or less answered by that kind of attitude. Andrew Jaffe says, what are your thoughts on idealism? When you consider a material explanation for the universe, it's difficult to comprehend exactly where our space exists relative to other possible spaces. Could it in fact be, as idealists may contend, much like a dream, where the actual space of the dream is in someone else's head in bed? I attach almost zero credence to idealism. Idealism, for those out there who have avoided this, fortunately, in their lives, idealism might be opposed to materialism or dualism as a theory of the relationship of the mind to the physical world, okay? A dualist thinks that there is something mind-like, something world and matter-like, and they interact somehow. A materialist thinks there's just the physical material world, and the mind is sort of an emergent thing that comes out of that. Whereas an idealist thinks that there's only the mind, and the physical world is just a way of mind or minds. There's different versions of idealism, but a way of mind sort of organizing their thoughts about the world, okay? And to me, that has zero pull as a fundamental view of reality, and not for very sophisticated reasons, for like the most basic obvious reasons. Namely, it certainly seems like different minds construct more or less the same physical world. Like my friends don't have different ideas about what the laws of physics are than I do. Why is that? And I'm sure that a good idealist can come up with perfectly reasonable reasons why it's like that, but I have an even better reason why, namely because there really is a physical world out there. And I also think that once you understand the physical world and how it works, it's very natural that things like minds would arise within it. So I don't really think that idealism is in any sense attractive. There's plenty of work to be done in understanding materialism and physicalism. Andreas Kelly says, what's your favorite movie that doesn't have anything to do with science or science fiction? Well, many of my favorite movies have nothing to do with science and science fiction. Probably my favorite movie is Casablanca. I know it's not very original. I'm not being very clever here, saying that Casablanca and Pride and Prejudice are my favorite stories ever, but they're classics for a reason. And I think that these are things that I can just go back to over and over again. I almost said Brazil, which is another favorite movie of mine, but I realized that that's probably science fiction, isn't it? It probably counts as science fiction. But so let's just go with Casablanca. I would easily take, depending on the mood, right? I would take The Sting as another example of a movie that I could just watch over and over again. Michael Schillingford says, in a naturalistic context, there are many sensationalistic claims that frequently draw a lot of attention. In science journalism, the word illusion is a word frequently tossed out with regard to just about anything we deal with in our daily life, whether it be chairs, consciousness, colors. Do you think sensational claims and hyperreductionism vocabulary play a larger role in why some reject naturalism? So I'm not 100% sure I'm appreciating the question here, but I think what you're saying is that there are people who claim or are naturalists. That is to say, they think that there's only one world, the natural world. There's no extra supernatural world. And those people sometimes refer to things that we know and love, like chairs, consciousness, colors, as illusions. That is, and you're wondering whether or not this is overly sensational. So I don't. It doesn't really affect my feeling about them to think that they're overly sensational. I think that people who make those claims are generally just trying their best. They're trying to understand how the world works. As someone who works on cosmology and quantum mechanics and relativity, I am well aware that doing our best to understand how the world works can lead us to making statements that to someone who hasn't studied these things seem bizarre and way out and sensational, right? But if we think they're true, we should make them anyway. So the charge of overly sensationalizing things is not a one that I worry about too much. Now, I also don't agree that it makes sense to talk about these things as illusions. To me, when you say something is an illusion, it's a trick. It's giving people the impression that something is there when it's really not. And I think that things like consciousness and free will and chairs are there. They're not illusions, okay? Now, I know what they mean. What they mean is that these things, chairs or free will or whatever, don't have fundamental essences. They really just mean they're emergent. That's really what they mean. But I don't want to attach the word illusion to emergent things. I think emergent things are just as real. Why? Because they give us a handle on reality, because they help us understand what is going on and make predictions. That's the criterion for being real. Like if you are starving in a desert and you think you see an oasis and it's just an illusion, that does not give you a useful handle on reality. That will cause you to crawl toward that oasis and you would be wrong, okay? So that's an illusion. You're actually being tricked, and thinking that it's there is hurting you in your attempts to make it through the day and understand the world. Whereas chairs and consciousness and colors, I think, help you get through the world, get through the day. Paul Hess says, does dark energy deserve to be part of the pie chart of the composition of our universe along with dark matter and baryonic matter? It seems very different from the other two forms of matter. The amount of it doesn't seem to be conserved as space expands, and it doesn't seem to be interchangeable with matter. If it turns out to be cosmological constant, is it even an energy at all? So the answer is yes, it is an energy. Sorry, you asked two different versions of the question. It does deserve to be part of the pie chart. Yes, it really is an energy in a very, very specific sense. That sense is we have an equation for the evolution of the universe. The Friedmann equation, derived by Alexander Friedmann soon after Einstein invented general relativity. And the Friedmann equation, so part of general relativity, it relates the expansion rate of the universe to the amount of energy in the universe. H squared is proportional to rho, where H is the Hubble parameter and rho is the energy density. And if you want to fit the data, you better do what general relativity tells you to do, which is that into that expression for the energy density, you better put matter and radiation and the vacuum energy, the dark energy. They better all be there, okay? And the reasons that you're giving to maybe be suspicious don't actually really hold up. So you say the amount of it doesn't seem to be conserved as space expands. True, but same thing is true for radiation. The energy in radiation goes down as space expands, and we still need to count that as energy. And then you say it doesn't seem to be interchangeable with matter, but that's not true. If you believe in inflation or false vacuum states or anything like that, there are very straightforward physical mechanisms that convert dark energy into ordinary matter and radiation. So yeah, by all ways that we have of thinking about what should count as energy, dark energy should count. Bits plus Atoms says, given that we don't live in anti-de Sitter space, why do many scientists believe the ADS-CFT correspondence is so important to understanding quantum gravity? In other words, what provides the hint that ADS-CFT may generalize? Well, the way that I like to put it is, if in my more cynical moments, you know the old story of the drunk guy looking for his keys under the lamppost, and the guy tries to help him and says, I don't see him anywhere. Are you sure this is where you dropped them? And he says, no, I dropped them somewhere else, but the light is really good over here. So ADS-CFT is the world's brightest lamppost when it comes to quantum gravity. The point being that we understand ADS-CFT. It's a known model, at least in a way that is much, much more precise and spelled out than we have models of quantum gravity in other cases. So it's not that we have good reason to think that ADS-CFT will generalize. We have reasons to hope it will, let's put it that way, but that's different than a good reason to think it will. What we have is the ability to ask questions and answer them. And that's just incredibly valuable, right? You can get wisdom. You can learn things about the general way things work by having solvable models, even if those solvable models do not extend directly to the real world. It's, again, the spherical cow philosophy. And I would understand and maybe even be sympathetic to people who say that we spend too much time thinking about ADS-CFT because physicists get happy when there are equations they can solve, right? They're less happy when they are struggling with ideas and not sure what equations to put down to paper. They're happiest when there are equations that they can write down, put into different contexts, get out solutions. And that's the case in ADS-CFT. It's not the world, okay? But what you're hoping is you get some wisdom about how quantum gravity works in this one case where you think you know how quantum gravity works. It doesn't seem to make sense to say, well, I would rather have 0 cases where quantum gravity works. At least you have this one. So I think that it makes absolute sense to put a lot of effort into ADS-CFT. I just don't think that it should be the only thing you put effort into. You really need to, and many people do, try to push beyond into other contexts. Tyler Ogorek says, feel free to pass on this question if it's too personal, but what drove your and Jennifer's decision not to have any children? Was it the plan from day one just to be the two of you, or was this a decision that was reached over time? What is older married life without children like? Older married life, I noticed you sneaked the word older in there, and I will let you get away with this time. I certainly am older than I used to be, I guess. But older married life without children is awesome. I love it. And look, I love other people having children too. So there are personal aspects to questions like this, which we can set aside, but there are also big picture ethical, moral, social questions, right? Is there some moral obligation to either have or not have children? And I think roughly the answer is no. I think that there are people who claim that there is, but I find their arguments entirely unpersuasive. So our decision to not have children was something that we always had. It was just always our personal preference. It was not like either something that was forced upon us by circumstance, nor was it some kind of big picture moral social stance. It's just that neither one of us wanted kids. We had other things to do, and we're doing them, and we're very, very, very busy doing them. And having kids is a lot of work, and there's a lot of benefits to having kids and a lot of downside, and there's a balance, and everyone should make that balance individually. I don't think there's any obligations, big picture, socially, either way. Emmett Francis says, I finally went back and listened to your first Mind Chat with Philip Goff and Keith Frankish. That was someone else's podcast I did, either on YouTube or audio, with Philip Goff and Keith Frankish about consciousness. And so Emmett's saying, one follow-up question, could there be a type of consciousness that has no causal influence but still matters in some sense? To use a crude metaphor, maybe consciousness is more like someone watching a movie. The observer has no causal influence over the effects on the screen, or the events on the screen, but it still matters that there is someone there doing the observing, perhaps. Well, there could be things like that, I suppose. That sounds nothing at all like the consciousness that I know and love. A part of our consciousness is absolutely related to how we act in the world. Of course, you can imagine people who might be paralyzed or somehow disabled to the extent that they cannot act in the world and still be conscious. That's right. But if you have the ability to act and you are conscious, I think that those are related to each other. So I'm not sure. You can imagine things like what you're suggesting, but I'm not sure if it sheds any light or is relevant to the questions that Philip and Keith and I were talking about, which is trying to come to a better understanding of the good old consciousness that we know and love. Herb Berkowitz says, there was an earlier controversy about whether the Webb telescope's name should be changed because of allegations relating to alleged behavior of James Webb vis-a-vis members of the gay community. NASA decided to leave the name of the telescope unchanged, but now the controversy seems to be flaring up again. What is your take on this specific dispute? So I guess there's the sort of big picture question here and the specific question being James Webb himself, the bigger picture question about what do we do when we realize the people who we are honoring by naming things after them are less good people than we thought. So about James Webb, I'm not an expert. I'm not a super duper follower of the give and take about people trying to investigate this. From what I have read on both sides, it seems that he was pretty involved in, there was a set of episodes back in, I guess, the 50s and 60s where gay people were sought out and purged from the federal government or from certain agencies thereof, and Webb seems to have been not the boss of that, but going along with it and abetting it, as far as I can tell. It's hard to tell sometimes because people were cagey about what they wrote down and so forth. But also, the telescope never should have been named after James Webb. That was a bad idea. James Webb is not a scientist. There is a difference between, parenthetically, this is a slightly different issue, but there's a difference between using a name as just a label or almost a citation, right? Erwin Schrödinger is under current discussion about whether or not he was a pedophile, whether or not he liked young girls younger than what we would now consider the age of consent. And I don't think there's any reason to rename, even if it's all true, no reason to rename Schrödinger's equation anything else because he did invent the equation, right? It's not like we're honoring him. That's not the point of calling it Schrödinger's equation. We're just mentioning the historical fact that he wrote it down first. Whereas James Webb did not invent this James Webb Space Telescope. It was specifically meant to be honoring him, but he was not a scientist. He was an administrator at NASA and other places. And the importance of administrators at NASA and other places is very, very high. Like, I do not want to say that it all could have happened without them. There's absolutely a role being played there, but I preferred it back when telescopes were named after people like Hubble and Chandra and so forth, Fermi, scientists who are really using this kind of data to understand the world better. So I leave it to others to judge the specifics of the biography of James Webb, but if it is true that he was involved in that kind of behavior, then I'm completely in favor of changing the name, even if it costs a little bit of money. Lewis, I should say, before going on to Lewis's question, one of the points of this is you could say, look, who cares? There are people who are the general public who are interested in the science coming out of JWST. They don't know the biography of this guy. What difference does it make? And the difference it makes is that there are people who are gay or otherwise in various kind of minority groups that have historically been discriminated against who take this as a message, and rightfully so. The message being, we don't care about you or your feelings, right? And again, this is all conditionalized on whether or not you do think that James Webb was involved in this. But if you do, then I think it's pretty clear that you should take action to not let this kind of thing happen. And even if it is difficult to rename the telescope, it is worth it trying to, send the message that these people do matter, that people who might be different than the standard 1950s nuclear family ideal are nevertheless human beings with the same rights and dignities as everybody else. And they haven't always been treated that way, and it's important to do what we can to fix that. And this, if it's possible to do so by things like this, then let's do it. It wouldn't fix everything, obviously, but it might be a nice gesture in that direction that we at least are trying to make things better. Okay, Lewis, your question gets finally answered. Lewis Wawaru says, what is a belief you once held that has changed during your adulthood, and would you reflect on what it was like if you can? For example, was it a matter of being wrong or naive, the longer held and most recent, if that needs a selector? I change all sorts of beliefs. The obvious things to change are scientific beliefs when there's just new data that comes in. I used to believe the cosmological constant was 0. Now I don't. There's also more, science-related beliefs, but nevertheless judgment calls. Like, I used to be in the crowd that objected to kicking Pluto out of the solar system planet club. I mean, Pluto's still in the solar system, but now it's a dwarf planet, not a planet. And my argument was that, look, we made up the word planet, right? We can make it up to be whatever we want. And we can always grandfather in Pluto, even if we come up with a definition for the word planet that is consistently applied going forward when we discover new planets around other star systems. That doesn't mean we couldn't just grandfather in Pluto and say, like, it's an honorary planet or something like that. But after, having Mike Brown on the podcast and reading his book and talking to other people and thinking about it, I do get it. I get why it was useful to rename it, to relabel Pluto. And it's not that Pluto changed, obviously, it's that we understood more about what kinds of objects there are in the solar system and elsewhere. And, the argument that I liked the best was from Mike Brown, who said, look, if things like Pluto count as planets, then he, Mike, would be the greatest planet discoverer of all time because he's found various other dwarf planets out there at the edges of the solar system. But those other guys don't really deserve planet status, and therefore Pluto does not. And there is something to be said for scientific consistency on questions like this. That's a relatively recent one. Other kinds of non-scientific things, I used to be a moral objectivist. I used to think that there was a science of morality, and you could derive true statements about right and wrong from is statements about, evolutionary biology and what people want to do and things like that. And it was just an improved philosophical understanding that let me realize that was not going to happen. Wei Li Woon says, concepts like the block universe, arrow of time, multiverse have profoundly changed how I view the world. For example, fully embracing the block universe view could allow one to take a more philosophical view when dealing with life's challenges or personal tragedy. In a similar sense, do you feel that your deep knowledge of physics has changed your approach to life? And more importantly, are there concrete examples of how being a theoretical physicist has guided your everyday actions? I think that the most honest answer here is no. I can't think of anything specifically that is a way that I act or feel that would be radically different if I knew less physics. I think, the honest answer, if the honest answer to this were yes, I would have to be able to come up with an example of some way that I got through life that just wouldn't have been available to me without knowing physics. I can't honestly think of that. Now, having said that, I'm sure that knowledge of physics has seeped into various beliefs and ways of living that I have in ways that I don't even know about, right? Certainly the biggest one is the absence of God in the world, which is related to scientific understanding in various ways. And that's why, with my friends who are scientists and philosophers who don't like talking about God, who are atheists, right, but think that it gets in the way of talking about science when we talk about religion, I think that's a mistake because there isn't any other more direct relationship between our scientific understanding and the meaning of life than to decide whether or not God exists. Whether or not God exists is an important question, and science bears on that question. And so I think we should talk about it on one side or the other. I think that non-atheist scientists should also talk about it. But anyway, I don't think that you need to know a lot of science to become an atheist or to believe that life's purpose is something you generate for yourself rather than being imposed from elsewhere. So I don't think there's a very close connection there. Arnie Moskowitz says, it is generally agreed that a regular amount of physical exercise is not only essential to maintain health, but it is believed that increasing the blood flow to the brain will actually improve intellectual output. So I'm afraid to ask, what is your exercise routine? I'm not actually up on the evidence one way or the other about physical exercise and intellectual output, but it's a very plausible story. So I'm not going to deny it. It's very believable that, so there's a joke that went around. I'm not even sure if it's a true story or just made up, but a graduate student was, kind of poo-pooing the need for exercise or physical activity, and their advisor says, what, are you a dualist about the mind and the body? And they say, no, I'm definitely just a physicalist. And then, then the mind comes from the body, and then you want to keep your body in good shape. And again, that's not a scientific hypothesis that has been rigorously tested, but it makes perfect sense. And there is, of course, some evidence for it. So therefore, I do think it's important to exercise, and I don't do as much as I should, but I do try to exercise. Jennifer, my wife, is an exercise aficionado, fanatic, I don't know what the right word is, a regular. She exercises all the time. She has a black belt in jiu-jitsu, and She has never told me that I need to exercise myself, but I do exercise myself sometimes, and she inspires me to try to do better. Let's put it that way. So I try to actually go to a gym or something like that a couple times a week. When you're traveling or when you're moving across country, that becomes very, very hard. There is an app that I found that is kind of fun called 7, like the number 7. I'm not getting any money from it, not advertising it, but it's just a simple 7-minute, or it's really 8-minute exercise routine you can do in your hotel room, right? There's no weights or equipment involved. And if you want to, you can do it 2 or 3 or 4 times in a row if you're feeling that energetic. That's not a lot of exercise, obviously, less than 10 minutes, but getting the blood flowing just a little bit is helpful. I have recently switched to standing desks that I can move up and down, so I can sit or stand at my desk. I like the fact that I can do either one. Otherwise, I would just be sitting down all the time. When I am actually at the gym, it's just a mismatch of different things. I do some cardio, lifting weights, various flexibility, yoga type things. When I'm in the vicinity of a good yoga place, I will go to yoga classes also. And because sitting down for long periods of time, typing at the computer is just not what the human body was meant to do. And yoga is almost as if it were invented to make up for the strains that you put on your body when you do that kind of thing. So I highly recommend it. Jacob Arkin says, in episode 9, on the solo episode on Why Is There Something Rather Than Nothing, regarding your early interest in big ideas, you said, I forgot, by the way. Yes, we were talking about that, weren't we, in the AMA, that I mentioned that I wrote a paper on that. It is also true that I did a solo podcast on it. So if you're more audio friendly than text friendly, check out the podcast on that. Anyway, Jacob says that I said, quote, when I would fall asleep at night thinking about something that I've read in a cosmology book or whatever, at some point my brain would come onto this question of, what if I weren't even here? What if the universe was not here? What then? And then that was it. No more sleep for me that night. That was the kind of thing that kept me up at night. That and Bigfoot, but that's a whole nother story. So what's the story about Bigfoot? Jacob asks. All right. This is how much I appreciate you all out there in Patreon and podcast land, helping me with the donations and leading to the AMAs, that I will tell you the Bigfoot story, which is that we were moving from a tiny apartment to a not very large, suburban house in Pennsylvania. And I was like 8, 9, 10, something like that, at that kind of age. Okay. And I had a younger brother. And so for the first time in our lives, we were going to get separate bedrooms. This was very exciting because we used to, when we were younger, we would just have bunk beds in the same room. And as the slightly older brother, I get to choose which bedroom I was going to get. And there were basically 2 choices. There were 3 choices. There was a relatively large bedroom, relatively small bedroom, both upstairs with the other bedrooms. But there was also a sort of a den downstairs that could be used as a bedroom. Okay. And the obvious, sensible thing would have been to go for the larger bedroom upstairs where all the bedrooms were. But I thought it would be, cooler to be far away from everybody else and have my privacy. And therefore I went for the den downstairs and converted that into my bedroom. And within weeks after we had moved, I forget whether we actually went to the movie theater or I just saw it on TV, but I saw a documentary. I hesitate to call it a documentary, but it was about Bigfoot. And it was, a pretty credulous documentary, basically making the case that Bigfoot was probably real. There was all this grainy footage and reenactments. And for my 9-year-old or whatever self, that was really scary, even though it wasn't meant to be scary. It was meant to just be, ooh, look, Bigfoot. And Bigfoot is also just not that scary, right? But it wasn't, science fiction or fantasy. It was something that was plausibly real. And so my subconscious reacted badly to the existence of Bigfoot. And being alone downstairs in the house all by myself on the first floor of our suburban house, I could, look outside and see trees and hear noises that I couldn't recognize. And I became afraid that Bigfoot was going to be outside. Now, even at that age, I was perfectly rational enough to know that that was completely silly. Bigfoot didn't exist. And if Bigfoot did exist, he would not be trundling around the suburbs of Philadelphia in Pennsylvania. Nevertheless, there's a part of your brain that is not the logical, rational part, and I just didn't want to stay downstairs all by myself anymore. So I moved back upstairs, but of course, by that time I had lost the good bedroom, and so I was stuck for the next whatever years until I graduated high school in the smaller bedroom upstairs. There's a lesson there of some sort, but I'm not exactly sure what it is. Matt Rappaport says, recently, I was listening to a science podcast that seemed to suggest there are a number of cracks forming in the standard model. They cited 3 findings. Number 1, mass of the W boson. Number 2, magnetic properties of muons. Number 3, excess production of heavier quarks than predicted in the standard model. Do you think that experimental data is beginning to show cracks in the standard model? Well, I don't know. I think that all of these 3 examples are different. And there's another one that I think you're not mentioning. I think that you're not mentioning it. Anyway, remember I did a solo podcast a little while ago about the muons in particular, because you're mentioning one muon experiment, the one at Fermilab with the magnetic moment. There's also an experiment, I think at the LHC, on the decay of the muons, violating flavor universality, like acting differently with respect to different flavors of particles that it's decaying into. And I think that those are relatively respectable anomalies. So just so you know sort of how to think about these things, there are always anomalies. We do many, many experiments. If you do 100 experiments, you expect to see a 1 in 100 anomaly sometimes, right? And of course, you then begin to study that particular anomaly more closely, et cetera, et cetera. And people get excited and they write papers about what it could be and et cetera, et cetera. So the very fact that there are anomalies does not by itself make me think that there are cracks in the standard model. There always were and always will be anomalies. They have to become really, really strong for me to get excited about them. In the muon case in particular, probably the strongest anomaly in the sense of disagreement between theory and experiment seems to be the magnetic moment of the muon in a believable way. The W boson mass I'm not that excited about because it's incompatible with other measurements, including measurements by the same detector in earlier years, and it's based on 10-year-old data, et cetera, et cetera. It could be true. The people who are doing it are good people, good physicists, but it's hard to do that. And when it doesn't fit in together with other experiments, then your guess is that they're just missing something, right? That might not be true, but that's a guess. Whereas the magnetic moment of the muon seems to be pretty solid, except then you read the fine print, and what you find is that there is a calculation with regard to what the magnetic moment of the muon should be that involves QCD, the strong interactions, which is always very, very hard to calculate in. And they do the best they can, and they get this discrepancy, but there is an alternative way of calculating that makes the discrepancy go away. And that, it's always just the safer bet to think the discrepancy is going to go away. Eventually, some discrepancy will not go away, but I don't think that any of these discrepancies are quite strong enough that I would bet at 50-50 that they are going to last. But we have to do more experiments, collect better data, and then we'll know. Lester Sue says, one of the questions from your last AMA regarding democracy and course correction got me wondering. Are societies that place more value on stability, particularly those with autocratic governments, more prone to instability in the long run? Have you considered this, or are you aware of any research considering this? And in particular, do you think there might be similar physical systems that one can draw useful comparisons with? So no, I've not considered it, and I don't know of anyone who's considered that, but it seems to be a very difficult question to ask all by itself. The number of societies that have existed in history is not that large compared to the number of events we see at the Large Hadron Collider or something like that. And you could try to compare the long-term stability of dictatorships versus democracies, but not only is there very little data, but there's so many other factors that matter, right? The democracy in Athens is very different than the democracy in Rome, which is very different than the democracy that the Iroquois had, which is very different than the democracy we have here in the United States for all sorts of reasons. So I would just be skeptical that you could focus in on that one variable and draw any close comparisons. Jake Cornegay says, whenever I see a physicist describe what would happen if a person were to fall into a black hole, they always talk about spaghettification, or how you wouldn't even know you'd cross the event horizon in the case of supermassive black holes. I understand simplifying things for the audience, but what would really happen to a person entering a black hole in a spacesuit? Would tidal forces strong enough to pull the person apart near the event horizon kill them by exposure to space as the suit ripped apart? Or would spaghettification stretch the person and suit together such that the person would live long enough to experience a painful demise from the spaghettification? Well, I don't know is the short answer. There's an engineering question here about the tactile strength in your spacesuit and things like that, which I am completely ignorant about. But I do know, the prediction from classical general relativity of what would happen in the black hole. The point of the spaghettification talk is that it doesn't happen near the event horizon. That's not where it happens. It happens when you approach the singularity. If the black hole is small, and again, the singularity is a point in your future, so that's okay. You can still approach it. You just approach it in time. If the black hole is small, the singularity is close all the time, and as soon as you get to the event horizon, you're already close to the event or to the singularity, and there can be spaghettification. The point of spaghettification is any object is pulled in one direction, the direction that is sort of pointing inside the black hole, and squeezed in the other two directions. So it is differentially torn apart, and that happens to both you and your spacesuit equally. Okay, so then there is a question about, does the spacesuit hold up? Like if the spacesuit stretches by 20%, maybe it still maintains its airtightness. But if you stretch by 20%, I suspect you die, right? But maybe, I don't know, maybe your spacesuit is weaker than you are and your boots fall off before you get stretched so much that you die, and therefore you would die from the loss of air. I don't know the details. What I do know is when you approach the singularity, you get stretched. That's the spaghettification. Josh Charles says, after listening to the wonderful quantum steampunk episode, I went and got the book. Near the end, there was a discussion that seemed to connect the uncertainty principle with the second law of thermodynamics. Am I right that there is a connection between these things? And does this mean that there could be a sense in which the uncertainty principle leads to the arrow of time? Well, there's a connection, but there's not a necessary or a strong connection. Let's put it that way. I mean, the second law of thermodynamics was invented long before quantum mechanics was, right? Boltzmann understood the second law of thermodynamics without knowing anything about the uncertainty principle. And usually when we do a textbook explanation of the second law, or the kind of explanation like I did in my book From Eternity to Here, it's all perfectly classical. There's nothing in there about the uncertainty principle or any other quantum mechanical effect. Of course, the world is quantum. The world is not classical, so all those discussions are merely approximations to what really happens. And I think that the relevant thing to say is that when you are in the regime where quantum effects are important, then you can have a relationship between the uncertainty principle and the second law. But when you're mixing cream into coffee, you're not in that regime. There's no importance in quantum effects or the uncertainty principle or anything like that. And, by the way, I say this over and over again, but the arrow of time is explained. It is explained by the definition that we have of entropy from Boltzmann and the fact that the entropy in the early universe was low. Those two things together explain the arrow of time. What we don't have explained is why the entropy of the early universe was low, and I don't see any direct connection between that and the uncertainty principle. Bart Connolly says, I have a question about materialism. I've noticed that statements made by materialists usually include the word just as in synonym for mere or insignificant. Yet if you remove that word from such statements as humans are just robots made of chemicals, you get a much more profound and even pantheistic statement. Humans are robots made of chemicals. My favorite is, of course, we are just the universe observing itself, which I really prefer to be, we are the universe observing itself. I'm not throwing proverbial shade on materialists, as I often agree with them. Rather, I just think, as it were, the materialist statements are a lot more positive once you remove that silly word. What do you think? Yeah, I'm somewhat sympathetic to this. I get it. The meaning is the same either way. I think back, not always, I shouldn't say that, but Julia Galef, who was a former podcast guest, she had a very good tweet a while back where she says when she's reading news articles and she sees someone quoted as saying, Professor X admits blank, she always in her mind translates admits to says because it's the same substantive content. The person made this statement, but it's not trying to put some kind of normative or evaluative spin on it. And that lets you decide for yourself how to judge the words coming out of someone's mouth. And I like that because I've been that it's been done to me. Like I've said things like, we don't know how the universe began. And I'm quoted as saying, Carroll admits that we don't know how the universe began. I'm like, well, it wasn't much of an admission. I wasn't, trying to hide the fact. I say that all the time. Likewise, the word just in these sentences isn't adding any extra substance, right? I think, Bart, you're completely correct. You could just take it out and you'd be just, as it were, as correct. But I get why people add it there also, because it is a comparison, okay? So when you say, human beings are just robots made out of chemicals, you're comparing that statement to another possibility, namely that human beings are not just robots made out of chemicals. Like if you're a dualist, if you are Descartes and you think that human beings have a relationship between an immaterial mind and a material body, then human beings are more than robots made out of chemicals, okay? So the word just is indicating the fact that in the alternative picture, there's something extra there. And the materialist is saying, no, there is nothing extra there. Of course, for different rhetorical purposes in different conversational contexts, you may or may not find it useful or helpful or wise to use that word or not. Tamim M says, we come up with dark matter to explain the mass and gravity that is not explainable by stuff we see. What if it is just stuff that is behind what we see, just planets hiding behind stars or more stars behind very luminous stars? So the short answer is, we would have thought of that. The professional astronomers and cosmologists would have thought of that. They really try very hard. But I'm answering this question for two reasons. One is that I do want to emphasize that nobody wants there to be dark matter. It's never like we hope there's dark matter out there. Let's find reasons to believe in it. It is more complicated, less simple, less elegant and compelling to imagine a world with dark matter than a world in which the matter that we already know about explains everything we see. So it would be not much nicer. Your first guess as a good scientist is always that we should work hard to explain the observations we make in terms of things we know about. And astronomers and cosmologists and physicists do that, but they conclude that they can't fit the data by doing that, and that's why they're driven to posit dark matter. The other thing is that we measure how much dark matter there is, etc., by looking at stars and galaxies and their dynamics, but those are far and away not the only pieces of evidence that we have. In fact, the best evidence we have that dark matter is not ordinary matter comes from a combination of cosmological data with the cosmic microwave background, Big Bang nucleosynthesis, and so forth. Big Bang nucleosynthesis tells us the rate of expansion of the universe and the amount of ordinary matter in the universe when hydrogen was being converted into helium at early times, okay? So we know how much ordinary matter there is. None of it can be hiding. We have measured how much ordinary matter there is from the reaction products of nuclear fusion in the early universe. Then at the same time, using the microwave background and other pieces of data, we know the total amount of matter. We know how much matter there is from the CMB. We know how much ordinary matter there is from BBN, Big Bang nucleosynthesis. They do not agree with each other. So even if you ignored all of the data from galaxies, from clusters, from the growth of large-scale structure, all of that stuff, you would still have to believe in dark matter. And you would have to believe that dark matter is not the ordinary baryonic matter, hydrogen, helium, etc., that we know and love from our experiments. C. Branch says, debates are notoriously won by persuasive speakers with statements that are emotionally satisfying to the audience, like I said, by the way, related to what I said in the intro, regardless of the truth of the argument. Advertising, likewise, is an attempt to persuade the target audience to buy a product or support a candidate, rather than allowing them to make a decision based on facts alone. As a self-serving attempt to manipulate the thoughts and behavior of others, shouldn't persuasion itself be considered unethical? No, I do not think that persuasion itself should be considered unethical. After all, C. Branch, aren't you, by the phrasing of your question, trying to persuade us that persuasion should be considered unethical? Persuasion is just trying to get somebody to believe something to be true, right? That's what a persuasion means. That can be deployed for good or bad reasons. And when something can be deployed equally well for good or bad reasons, you can't assign it an intrinsic ethical valence as positive or negative. Persuasion can be used for good reasons as well as for bad reasons. I think it is essentially impossible to imagine a world without persuasion. You could easily characterize teaching someone math as trying to persuade them that the mathematical theorems are true and that these methods of proof are useful, and so forth. Persuasion can be misused, but that doesn't mean that it's somehow ethically bad. I mean, I could go on with examples, but I think you get the point of what I'm saying. M. Masella says, your enthusiasm in both tone and cadence in the use of the word stuff in AMAs always makes me smile. It makes me think of the classic George Carlin monologue on this subject. Were you by any chance a fan of his? Yeah, I was absolutely a fan of George Carlin. Not like a super fan. I don't have all the albums or whatever, but I always enjoyed his take on things. I thought he was both very, very funny, a great comedian, and I liked his attitude, his perspective on things, which you can't separate, right? I mean, comedians have angles, they have perspectives on things, and George Carlin and mine are very much compatible with each other. I know the monologue you're thinking about. What is the point of it? I'm happy to use slightly naughty language here. The point of it was, I'm not going to get the details right, but other people's stuff is their shit, and your shit is stuff, or vice versa. I forget what it is. But anyway, I don't think that my pronunciation or cadence of the word stuff is influenced by that, but it might be that I just don't know. It's not always the case that we know why we do things. That's why it's what I referenced just earlier about, what do I change my mind about? What impact does being a physicist have on my beliefs? These are not things that you can always pinpoint with a lot of precision. So maybe. Tim Giannitzos says, great podcast with Judea Pearl. You both agree that causation does not exist in fundamental physics because all physical phenomena work in the same way, whether being run forward or backward in time. I don't understand how this bears on the question. If I explain the trajectory of a particle as being caused by a collision it had at a previous time, why would you describe this as a convenient shorthand rather than just as a fundamental observation? Well, it in part depends on what you mean by causation, and both Pearl and I in that case were thinking of the cause and effect relationships that we observe in the manifest image, in the everyday view of the world. If you have fundamental physics with very few moving parts and everything is reversible, you might think, well, I can ascribe causality to what happened earlier and then say, if something like a collision had not happened that way earlier, then the present situation would be different. Therefore, it's a cause-effect relationship. But what you find is that the same thing works backwards in time, right? I can say, well, because I will in the future have a certain collision, if I weren't going to have that collision, I must be on a different trajectory now, and therefore my trajectory now is caused by that future collision, okay? If you can say it one way, you can say it the other way, and therefore whatever you're talking about is not the everyday notion of causality. In our everyday notion of causality, causes have to precede effects, and it's not just a convention, right? It's not like, well, we chose it one way or the other. There's a reason why that is true. We think we have causal influence over events in the future, but we don't think we have causal influence over events in the past. And that kind of distinction wouldn't be possible at the level of fundamental physics. It is crucial at the level of the macroscopic world, and therefore we have to explain why. Jimmy Summer says, I've recently revisited Searle's Chinese room thought experiment, and it's much more interesting to me now. I know about the universality of computation, so in my view, there's nothing inherently impossible about simulating a human brain, and therefore all the phenomenology that comes along with it. But I'm still not sure what the correct response to the Chinese room is. If I might ask, what's your best guess at what's going on there? So for people who don't know, the Chinese room thought experiment from philosopher John Searle says, imagine a gigantic warehouse full of punch cards and other, very low-tech things. And there is a person who is an English speaker in the house, and all of the punch cards are relationships and computations that relate to things that can be said in the Chinese language. So there's an input, people put in little other cards that have Chinese characters on them, and this English-speaking person inside, I hope I'm getting it right, the description, goes through some procedure to relate that card to other cards, maybe moves some cards around, has memories or whatever, and then spits out some response that is also in Chinese. And what Searle is saying is, look, the person who is doing that, the actual agent that is moving around and shuffling the cards, they don't understand Chinese, right? There's something missing in the idea of comprehension of the Chinese language in that kind of thought experiment. And of course, what he means is that you materialists think the human brain really is like that, right? Some stimulus comes in, sensory input, and it goes through our brain in some mechanistic algorithmic way, and then we spit out a response. So he wants to argue against that as being true understanding. He wants to say there's more to consciousness and understanding than that. And of course, there's an extremely obvious response that was made right away, which is, sure, the person inside the Chinese room doesn't understand Chinese, but the room understands Chinese. And the only thing that the whole thought experiment is doing is trying to make consciousness in a materialistic sense seem silly by intuition pumping on our feelings about computation, right? You know, the human brain has, 85 billion neurons and some trillions of synaptic connections between them. And you can say, oh yeah, just imagine replacing neurons by punch cards in a big room. That room would be really, really big. And the speed at which these computations go is much, much faster in the brain than they would be with a little dude moving cards around, okay? So because it is so far outside our usual experience, to us, that doesn't seem like a conscious creature. But all he's done is do a one-to-one map between what goes on in real people and replace neurons with punch cards and things like that, okay? So if, like me, you think there's nothing more going on in the brain than what goes on in the neurons and our other cells and organs and so forth, then you have to believe that that room with a little person in it understands Chinese. And I have no trouble believing that whatsoever. So I see no impact in any special way of the thought experiment. Okay, Rick Antle asks a priority question, and he's cheating a little bit because it is long. And remember, you're supposed to ask short questions, but I think that this once, because it's a priority question, I will answer it even though it's pretty long. So Rick says, I am part of a small group of accounting scholars who are deeply interested in theories of information and complexity. Virtually all the accounting scholarship on information relies either explicitly or implicitly on Bayesian-style analysis. While this approach has been fruitful in yielding some qualitative results, this lack of crisp quantitative experimental evidence and the lack of a model of information processing costs has greatly limited our progress. In an attempt to come at our issues from a new direction, we have been studying quantum information, superposition, entanglement, density matrices, etc. We are unclear about the relationship between quantum information models and Bayesian ones. There are two sides to this issue. Number one, does there always exist a Bayesian-type model with a classical phase space, a priori distribution, and Bayesian updating that it could explain any experimental results that could be explained within a quantum information model? And number two, if both quantum and Bayesian approaches are used to model the same phenomenon, does the quantum model imply restrictions on the Bayesian model? Okay, so I'm going to have to confess that I'm not quite sure what counts as the scope of what you're calling a Bayesian model. I mean, like I've already mentioned, Bayes' theorem is a theorem. It's a theorem about updating a probability distribution. And that theorem is 100% just as true in quantum mechanics as it is in classical mechanics. Now, quantum information is a different kind of thing than classical information. And basically the way in which it's different is mostly because of entanglement. There's other issues you can get into, but entanglement says that the information, if you have a composite system with subsystems A and B, then the information in the system as a whole cannot be localized so that it's the information in A plus the information in B, okay? That's the big insight in quantum information. So, for example, you can have an entropy. Entropy is an information theoretic quantity. There's an information theoretic version of entropy, is what I should say. It was first a thermodynamic quantity. But entropy is telling you how much uncertainty there is in your overall probability distribution. A delta function, a single point where you know exactly what the probability is, with exact certainty what the system is doing, has zero entropy. Whereas if you have a lot of uncertainty, it has a large amount of entropy. And in classical physics, therefore, if I have a box of gas, If I don't know what any of the gas molecules are doing, that's a lot of entropy. If I know precisely what all of the gas molecules are doing, it is zero entropy. Whereas in quantum mechanics, if I have, again, a bipartite system, that is to say a system with two pieces in it, A and B, I can have the following situation where I know exactly the quantum state of the whole system. So the system as a whole has zero entropy. But if I divide it up into system A and system B and system B separately have a non-zero entropy because they are entangled with each other. Whereas classically, that can't happen, because classically, if I know in a box of gas the position and velocity of every molecule, then I also know the position and velocity of every molecule in every subset of the box, okay? So there is a difference between quantum and classical information because of entanglement, and my guess would be, without quite addressing your question, but my guess would be that there is zero applicability of quantum information theory to accounting because this crucial property of entanglement just doesn't exist in the macroscopic world where accounting is relevant. So unless you're really doing accounting with respect to small quantum entangled systems, then I don't think it's going to be of any help whatsoever. Now, is there some analogy? Is there some way in which quantum information ideas can be helpful in understanding ordinary accounting practices, etc.? Maybe, but I'm a little skeptical there too, to be honest. I would think that you can do everything with ordinary classical probability theory perfectly well. It's possible that I don't understand enough about accounting to give you the right answer there, but that would be my guess. Sid Huff says, you have on several occasions defended the importance of philosophy in the search for truth, particularly regarding cosmology and fundamental physics. In the June AMA, you chastised Richard Feynman for his dismissal of philosophy as useless in this regard. Can you give us an example or two of ways in which you believe philosophers have contributed to our understanding of either fundamental physics or cosmology? Yeah, I can give you many, many examples. There's many historical examples. We've already talked about Einstein inventing general relativity, right? He was hugely influenced by philosophical ideas, especially by Ernst Mach and a sort of relational view about the nature of space and things within it. Boltzmann was very influenced by philosophical ideas. Obviously, Niels Bohr, when he invented complementarity in quantum mechanics, hugely influenced by philosophical ideas. I myself have been influenced by philosophical ideas. Philosophers have done a much better job than physicists at clarifying the issues and the possible solutions to things like the arrow of time problem and the quantum measurement problem. You can't expect philosophers to invent new correct theories of physics. That's not their job. They're not very good at it. Sometimes they try. I'm not very impressed with what they do, but I'm extremely impressed with how they tell you why your theory of physics is not right. It's cheating, or it has hidden assumptions in it, or it's intellectually inconsistent with other things about other things we know. Various ways in which you can do better. Physicists, as I said in the recent solo episode about the philosophy of the multiverse, physicists are impatient and sloppy sometimes. The multiverse is an example where I think that most physicists these days are getting it wildly wrong. And I don't think that philosophers have really put their effort into getting it right as much as they should. So I'm hoping for insight from philosophers in that case. But that's what philosophers are really good at. They're good at clarifying the conceptual underpinnings of things, and there are parts of physics that really can benefit from that. Rue Phillips says, I believe I've heard you say that it's reasonable to think eventually everything will end up in black holes, and black holes will eventually evaporate, leaving nothing but useless long wavelength radiation. What I don't understand is, why do we think everything will end up in black holes? For example, say a star or planet gets ejected from a galaxy and heads into intergalactic space. Then the space around that object is always expanding away from it. Couldn't it be possible that everything, including black holes, will expand away from it forever and leaving it to wait for proton decay? Yeah, that's possible. That's completely possible, but it's a tiny fraction, I think. I think most things will end up in black holes. Proton decay, by the way, is not something that we are sure even happens. We have good theoretical reason to think it does, but we're not absolutely sure. We do have equally good theoretical reason to think that even without proton decay, something like a planet or a white dwarf or a neutron star will quantum tunnel into a black hole. So even something like that, even without proton decay, things don't last forever. And you can sort of justify that just by thinking about entropy. Whatever kind of thing you have, if you have a planet, let's say, you can turn that planet into a black hole of equal mass, and the entropy will be higher. And then that black hole can radiate into radiation, and the entropy will be higher still. So if there's no conserved quantities or whatever, like electric charge, that get in the way of a process like that happening, if the process increases the entropy of the universe, eventually it's probably going to happen. So, I mean, it's a little slightly casual, approximate statement when we say everything falls into black holes, but it's not doing violence to the ultimate conclusion you draw from this. P. Walder says, what do you consider are the reasons for the success of science from the Enlightenment to the present day? Is it in essence a change of mindset to focus on Popperian falsifiability, Kuhnian paradigm shifts, Stravins's iron rule of the preeminence of empirical data collection, or something else? Well, I don't think it's any of those things because those are all very, very after the fact. Popper, Kuhn, and Strevens are all 20th century people, or 21st century in the case of Michael Strevens, who's a philosopher of science. But science was pretty successful long before that. I do think that there was a shift, but this is something where this is a job for a real historian of science, which is not me. But in these cases where you have both a shift in how people act and a shift in how they justify why they are acting, it's usually a complicated interplay between those two things rather than a shift in beliefs and then following that a shift in behavior. So I think that in the case of science, it wasn't that people sat down and said, okay, let's invent the scientific method and then started doing it. They started doing it, and then they sat down and said, what is this thing that is going on that seems to be so successful? Empirical measurements, hypothesis testing, things like that, being open-minded about different alternatives rather than trying to use deduction to derive the correct things. There's a various sets of ideas that go into the informal procedure that we label the scientific method. And it all kind of happened, but it's a mishmash. I mean, that's what history is very often like. I think that ultimately, if you have to give one single reason why it was successful in terms of people believing that this was a good thing to do, it's because it worked, right? This kind of reasoning paid dividends in terms of a better understanding of the universe. And so people began to think deeply about why it was working so well. And we're still thinking deeply about that. We don't completely know the answer. Okay, last question. This has been a good long AMA. Hope you're all getting something out of it. So for those of you who have stuck around, last question is from Lucas Brombink, who says, I was super excited to hear you'll be joining Johns Hopkins as a new faculty member. I'm sad to have missed you by a few years, but while I was there, I studied neuroscience and philosophy with a particular interest in the philosophy of science. What type of courses or material do you intend to teach? So thanks. I'm glad that you're excited. I'm excited too. My job title is Professor of Natural Philosophy, which I made up. There's no department of natural philosophy. It's just me. But in practice, what that means is I spend time in both the physics department and the philosophy departments, and I'll be teaching in both physics and philosophy. And I can teach, roughly speaking, whatever I want. And so I'm going to be teaching a variety of things, within physics department. Like when you teach a course, there still needs to be a department for it. You can't completely escape the bureaucracy of the university, but they're pretty flexible about, how they categorize different courses and things like that at Hopkins, which is good for me. So I'm teaching a first-year seminar on the physics of democracy, where we talk about how we can use ideas from physics, from phase transitions and condensed matter systems and complex systems to better understand society and how it self-organizes. The common thread being that both in physics and in democracy we have emergence. Right? We have collective behavior. That is the important connecting tissue there. And I'm also teaching an upper level seminar on the topics in the philosophy of physics, where I will talk about the arrow of time in quantum mechanics and the multiverse. Going forward, I certainly hope on the physics side of things to teach more ordinary courses like quantum mechanics or general relativity. I also very much would like to teach a physics course on complex systems. There's some good textbooks out there. I know a little bit about the subject, but I want to learn more. There's no better way to learn more than to teach courses about it. On the philosophy side, I'm easing into it by teaching stuff that I know very well in the philosophy of physics. But going forward, I would hope to, both teach more advanced graduate level seminars in some of these topics when we are able to attract even more graduate students in the philosophy of physics and postdocs. I don't know if it's been I know that I've mentioned on Twitter, I don't know if I mentioned on the postdoc here, but Janan Ismail, who was a former Mindscape guest and a leading philosopher of physics, is also coming to Johns Hopkins, and maybe some other people as well. So we'll have a very good group in philosophy of physics and related ideas. So I think that's going to lead to more people who are interested in those subjects coming to Hopkins. We'll have more advanced subjects on that. And then, ideas like emergence and reduction and complexity can also be taught from a philosophical point of view. And then what I would really like is to become good enough to teach more standard philosophy courses, maybe even, moral or political philosophy. Who knows? Logic, ethics, we don't know. I don't know. Who's to say? I'm a professor in the department. I can think about what is available there. And that's what is really, really exciting and fun to me. There's so many things that I would like to learn and would like to know more about and would like to talk to people about. And, that's what philosophers are good at. So I'm looking forward to it. So I am also very, very excited. I'm glad you are, Lucas. I'm glad everyone here has listened to this whole long thing. Thanks for your support, especially the Patreon supporters. I really do appreciate it. Thanks for everyone who listens to Mindscape, and I'll see you next week/month/year. Bye-bye.